So I threw together some notes. What I'm going to do today is I just type, okay? And I'm going to answer lots of questions. I'm going to lead you down a particular path. But I did actually write up some of this stuff. So if you want to read it more slowly, hopefully it's all there. So you can click on this on day one. Okay, so the actual URL will be hard to see because so it's dsi.ucdavis.edu, and then it's capital R, capital F, fundamentals, R fundamentals. Okay, if you can't find that, just let me know. Okay, it's just dsi.ucdavis.edu and then /R, capital R, capital F, fundamentals. Okay, so this is going to be weird. I teach a class. I have in the past for the last 10 or 12 years taught a class where we do a whole lot of stuff where I teach basic computational reasoning and we teach R, and then we do a lot of regular expressions and data manipulation and data analysis. But during that class, I actually slide in how R works. Okay, and this is very useful, but I'm not teaching that class anymore, and as a result, I'm not sure it's actually getting taught as to how R works. So this may be overkill for people. And I suspect many of you will think, I don't need to know this stuff. And the answer is you do, okay, because it makes life easier. Do you need to know all the details every minute of every day? And will you need some of the weird functions I'm using to actually show you how R works? No, but sometimes when you get stuck, they're very, very helpful diagnostic tools to actually lead you down to the right path. But I'm happy to answer questions about anything that about anything that I can, and I'll also tell you if I don't know. I have been working in R for about the S language, which precedes R, for unfortunately now I think it's 20-something years, which is, I never thought I'd say that about anything. Technically, I'm one of the developers of S and R, so I know a lot about what goes on the insides. Okay, and so. Maybe that's not a good thing. Maybe I'm going to show you too much about it, but I think this is a really useful thing to actually know how it works. And if you walk away knowing 70% of what we talked about, then that's probably just about right. If you walk away knowing 100%, you've probably nerded out and gone too far down into the details. But they are but we'll try to keep above those. So anyway, there's we'll go through some. There was two ways I was going to do this, and yesterday I switched. I decided which way will we go? Which will we start with? Okay, and most people will start with, let's go with the data types, the data structures, the vectors, and these things. We'll do that on Thursday. Okay, why? Because one of the things I want to show you is that R is extraordinarily simple. It's ridiculously simple. Okay, you only need to know basically one real thing, and because everything falls into that. It's a very uniform language. So one of the things I was going to do, but first of all, just yell if you have any questions. Okay, this is highly informal. There's no test. There's no there's no homework. There's nothing. I did put up some exercises which we may stop and take a break and do some. And they're just kind of explorations. Some of them will be blatantly obvious. Some of them will be, okay, go off and play. But just interrupt and say, I'm happy to take questions about anything. Some of them I'll just defer and we'll talk about later on. I'm much less interested in what I call vocabulary, which is, what function does this and what function should I use to do X and Y, whatever it is. That's essentially what we're interested in is grammar. A lot of how does this engine actually work and what does it process. And again, hopefully this stuff, if it's too elementary, let me know. I can ratchet it up a notch very fast. We can get into a lot of perverse details, but which we don't want to. But I suspect, and please correct me if I'm wrong, I would actually really like to know, that a lot of people learned R by sort of mimicking to some extent, or being told, oh, you use this function, you use that function. Data frames, yeah, good. As opposed to why data frames and why not matrices and why do you do certain things? Okay, so those questions I would love to answer. Okay, so just yell if I forget to talk about anything. And if you don't understand something, if you think it's really elementary, let it go. Okay, but probably it's not. Just ask me and I'll tell you later on or whatever it is. But for the most part, if you don't understand something, everyone else in the room doesn't either. Okay, properly, or it'll give me an opportunity to actually make it a stronger point. Yeah. Yeah, we actually are doing a recording of this as well, so I have a mic. If you have a question, wait for me to run through the mic before you ask it. So, yeah. Excellent, good. So let's. Your name? Caitlin. Kate. Caitlin. Let's get Caitlin some exercise. So here I'm going to start off with the world's, well, let's start off with the world's simplest thing. R is an extremely powerful and overkill of a calculator. Okay, but it illustrates all the points we actually need. What happens when you do that? Okay, or more to the point, when I do this. Can you all see this, by the way? Do I need to make it bigger? Okay, let me know if it's sort of, thank you. Always wanted the back. Okay, and now we sort of, okay, so what's R done there?
You actually move your screen just a little bit because it's
just off to the left. Yes, thank you very much. Oh, easier said than done. Happy now?
Yeah.
Good. Okay. So there's a lot of stuff going on here that just nobody pays any attention to, and they don't have to. And that's the beauty of these languages like MATLAB and Python and R. Okay. So what's going on here? This thing here is what? What's this called?
No.
This the greater than. Yeah. So in this context, it's not a greater than sign. It's actually what's called a prompt. Okay. We can change it to be anything you want, but it is actually a prompt. It's actually saying, give me some instructions. It's pointing. You know, the concept is it's pointing at here. Type here. Okay. You know, but you can change the prompt to be absolutely anything you want. Typically I do, okay, but not here, thank goodness. Okay, so this is what's actually called, and again, overkill, but it's kind of nice to know these things just in case any other people start talking to you about them. This is what's called a read, eval, print loop. Okay, why do I tell you this? Because that's R, and that's Python and MATLAB and all these interactive programming languages. They have this thing where they read input. Okay, they just read a bunch of text. Some of them are smarter now, but ultimately they all come down to this. When you hit return, they go, I'll suck up all that text and I will do something with it. What will I do with it? I will read it. Then I will parse it. Okay, then I will parse it and I will give you an error if it doesn't make grammatical sense. Okay, if it makes grammatical sense, I will then evaluate it. So this is the read, eval, print loop. The read and the parse go together. The evaluate then says, okay, I'm going to actually carry out the instructions as you think you intended. Okay, that's the evaluation part. And then it prints the result. And then the loop part of it is just, I'll go back and do exactly the same thing again. I'll give another prompt. Okay, I have my prompt tells me what number command I'm on, so I can go back. I don't think yours does by default. I had to tell it to do that. So what you've actually seen is here is this actually has read in just one character, well, two characters, one and the new line. It's parsed that. It's done something, okay, and then it evaluates that. Now we have to figure out how it evaluated it, and then it printed the result. And in R, it prints the results. It tries to actually put row numbers down and stuff like that, even when there's only a single scalar value. Everyone happy? How many of you knew what a REPL was, a read, eval, print loop, when you arrived here? Okay, two or three. Okay, so this is a come on. Hi, Adam. So a REPL is just this what goes on. Why is it marginally important to know this? Partially because there's two phases that go on. There's the parsing phase, and then there's the evaluation phase. And you can get an error in either. But if you get an error in the first phase, it's actually that you've got a grammatically incorrect piece of a command, okay? And that's a totally different thing from it running for half an hour and then failing later on, okay? Or that you've mistyped a symbol, but it's still a legitimate symbol. So you actually have to start thinking. Sometimes, you know, you look at it and go like, that makes perfect sense to me. It makes perfect sense to me. It makes oh, I see what the problem is, okay? And it's actually it's a syntax error, and it's kind of useful to actually know what goes on. Now, so there is a function. I'll just introduce this early. Okay, again, you will almost never ever have to use this function. This is one of those functions where this is very useful for understanding what's going on in R. This is what I just typed in, 1, and I hit return. So when I get this, okay, parse text, okay, I'll assign it. I'm assuming you've all used R. Okay, we'll talk about this on Thursday. I'm assuming you've all basically know how to make a variable. You know, you probably know where the variable goes, although we're going to talk about that very soon. Okay, so this is fine. I'm going to just say parse returns something. That's what parse is. Have you ever seen this? An expression. Now, most people never see an expression, and you don't need to see expressions. People like me do. Okay, I enjoy sort of playing with these things. Okay, but that's fine. But basically, you know, it's almost like a list. Okay, I can pull out the first element, and it's just 1. Now, what's actually happened there is, okay, and again, this is sort of all technical and nerdy. We'll go faster, quickly. But what R says, when it parses that, it actually looks and says that's a constant. That's a literal value. So it turns it into a literal value. Okay, what's the class of this? What's the class of E1? We'll talk about this on Thursday. It's actually already a numeric value. Okay, we don't have to do any computation to get the value 1. The parser actually said that's a literal value. I don't need to do any computation subsequently. That's a literal value. There it is. It's in the thing. It's in the parse tree. So when I try to evaluate a literal value, what should I get? Just itself. Okay, so that's the simplest command you can do in R. Okay, it evaluates literals. Pretty boring. Okay, look, tell me the answer for 1. Okay, this is excellent. Okay, so what about? Okay, so then we do something like the following one. Well, let's do this. What's it going to do when I do this? Because this is a different ball game altogether. And now all of a sudden we've gone from doing simple literals to symbolic computation. I've typed this in. I hit return. It's going to parse it. If I parse it, well, let's emulate it. Okay, partially because it is actually, you'll hopefully never have to do this, but if you do, it can help. It can help, or at least it helps you to think the way R is thinking. Okay, I've just parsed this. What's E? Okay, this is the annoying part of my screen. Always drops to the bottom. Okay, what's E? It's now just this. It's just essentially replaced the 1 with a pi, which it makes perfect sense. What's that? What's the class of that? Anyone want to tell me what the class of this guy is? You should not know. Anyone who does can come up and give the talk. No, but the nice thing about it is it's easy to find. Okay, R is extraordinarily reflective. You can ask it questions about what it thinks it's doing. What's the class? It's class name. It's not a string. It's not quote pi. It's actually a name. It's the name of what we call symbols. Okay, these are symbols. A name and a symbol are the same thing. These are essentially variable names. Okay, and now we've got an issue with every programming language you learn. When you have variables, the first question you ask is, okay, what is the rule for finding these variables? What is the scoping rule? Okay, and the answer. And now we've got a problem. Okay, because now it was easy because if I did 1 + 2, you all went, it was 3, and you go, that's fine. There's no variables here. Yes? No variables? No, there is a variable here. 1 + 2 is totally different from any other language that you most likely come across, where the compiler would automatically just say that's 3 and let's be done with it. There's a very good reason why plus, in this case, is a variable we have to go find. Okay? Okay, but it all makes perfect sense. Okay, so these 3 simple examples show you that there's actually an awful lot going on, I hope. Okay, but it is actually pretty straightforward. Let's go back to the pi version, okay? Hey, 3.1415, okay? Pi happens to be a built-in symbol into R. Does anyone know where it is? Where does R find variables? If this is cryptic, by the way, just yell at me. I mean, just ask me stuff. I'm sort of trying to prompt you that this is actually a little more subtle, very easy. This is a man-made thing. Okay, it's intended to actually be comprehensible and easy to use. Okay, we failed, but this is not, you know, sort of mysterious mathematics that may come from some novel unknown place. We constructed this. It's got a simple computational model, as simple as possible. Okay, so if anything's unclear, where does R find pi? Well, okay. Some of you will know about your global environment, your workspace. Okay, it ain't in there. Okay. We can type ls. This is what, by the way, we're at the prompt here. This is what I call a top-level command. These are very different from commands that go on inside other function calls and stuff like that, although they're very similar. But I call this a top-level command because when we're at the top level, LS refers to the global environment. When I make assignments, they go into the global environment, okay? So the global environment is very special, but it's for the top level working space. So if I type LS, I happen to have a few things in here. I've got E, I've got this, okay? Pi is not in there. So where did R find pi to give me 3.14? You could say it just knows certain constants. R is not built that way. R knows nothing. It doesn't know about plus, okay? So, because it's nice, because then you can change how plus works if you so desire, okay? Don't. Don't even change pi, okay? Although we're going to find out that it doesn't matter if you change pi, okay? Everything else will continue to work properly because it has built-in protection against idiots. Okay. Now it's there's good computational reason for keeping everything separate. So what is R actually doing here? I'll tell you where pi is. He said, hoping that he was correct. Okay, it's in the base package. Okay, so R is built in certain things, but the language itself doesn't know about pi. It actually has to go find pi. Okay. So how did R know to go? I typed this and I said, go look in the base package. In most languages, you have modules or packages, so to keep things in that are related in groups, okay? And you can look at those. What we've actually got here is I've said, go in and find pi, the symbol pi in base. Now, when I do that, there's actually still an evaluation. This is a REPL. R reads this, it parses it. If I parse it, we can take a look and see what it is. It's a variable. It still has to go find it, but I've told it where to look for it, so it has to go get it. And it actually has to go in and find the symbol matching pi and see what value it is bound to. Okay, or more to the point, which value is bound to it. So there's a difference between the value and a variable. A variable is just a placeholder, a name that we go back to, and the contents can change as we move along. Okay, so we have symbols or names, okay, and variables, all essentially synonymous, and we have values. This is a numeric value, okay. It's a literal value, so it came in as a literal at some point. We're not even calculating it, okay. But how did R go and find this? Let me just do one other thing. Pi is equal to 3, okay. So just change pi to be 3, and now just give me back pi, and pi is 3. Okay, so R is finding it differently now. Pi is not built in. Everyone happy? Okay, it's not built in. So where did I find it? Let me just get rid of pi for the moment. It's this guy here. It's the search path. Okay, and this is under your control, but by default R just creates a certain search path. It loads up always the global environment, and it is always the first thing in your search path. You cannot get anything else in there first, or the world will fall apart. Okay, then you've got all this other stuff. This is ESS, just loaded this for me, thank you. Okay, and you got stats package and so forth, and it went all the way to base. What does R do? Okay, and this is kind of, I'm going to show you this in 2 different ways. Okay, basically what R does, it says, I'm at the top level prompt, I'm looking for pi. So I look in here. Do you have the symbol or a variable named pi? No. LS of this? No. Okay. So when I put pi in here, the answer was yes. I found pi here. That's why it gave me back 3 here. Okay. Then I got rid of pi from here. So now pi is not there. So now I look in here. I look in here. I fail. I look in here next. I look in here next. I look in here next. Okay. And I go all the way down until I hit pi in base. Okay, and then what R does is it says, okay, there is a symbol named pi. Now I need to go and look it up, okay, and get its value and replace pi with the actual literal value. Okay, so I replace the variable with its current value. Okay, and that's all that's going on. That's what evaluation is doing. So we've seen 2 types of evaluation. One is of literals. The parser actually creates the literal, and the evaluator says, I have nothing to do. Excellent, I just pass it straight through. When we get a variable, the evaluator has to say, I have to go look for that variable, and then if and when I find it, I then go and have to get the value and return it. But I don't have to do much. There's no computation going on in terms of actually post-processing the value. I just have to then print it. So I go back to my read eval print loop. The evaluator is now, we know what the evaluator does. But the evaluator did actually have to go search this. Okay? Now here's something you do not need to know yet. But I'm going to tell you about it anyway. That is an environment. Okay, global env, the environment. Okay, that's what the env starts for. Okay, and you can actually access it as global env. There's a function that returns it. Environments are the heart of this language. They are simply this. They are containers, just big boxes or bags of name value pairs. Okay, so variable name and a value. Variable name and a value. Okay, it's just a big unordered collection. The order doesn't actually matter, but that's what they are. Just think about them as being a big table into which you look up the variable name and get the corresponding element, and that's the value. Okay, we don't care what the values are, so there can be lots of different values, but that's it. Okay, why is this important? Because they're how we work in our workspace. They're how we put variables in. They're how packages manage their own variables. Okay, and environments are also how functions work, how function calls work. So when you call a function, we create a new call frame, which is actually an environment. So we use the words differently. Call frame, environment, same thing. They're just where the local variables and the parameters live for the function, for that function call. So if you understand environments, you got most of R. Okay, because this is where we find variables both in function calls and just along the search path. Okay, so how does R know about this thing? Okay, what it actually does, and this is a special, I've told you the rule. It just goes through the search path and goes until it finds the thing. And if I wanted to, I could actually, there's an R function that says find pi, please. And it says, there you go, it's in package base. Okay, so it could just jump to package base. But how does find know to do this? What it actually does, and the reason I'm telling you this is because it becomes helpful when you understand, when you really want to understand what functions are doing. Okay, this guy is chained to this guy, is chained to this guy, and so forth. And I can actually walk my way through this. I can ask for the parent.env of global env. Okay, give me the global environment. That calls a function. I haven't told you how that function works yet. Okay, I'm skipping bits here. Okay, but global env, parent env says, get the global environment and ask us for its parent environment. Parent environments are weird, by the way. They're so important, and they're the one thing that kind of defies the basic rule in R about copying everything. But basically, what's it doing? Look, you see, it's ESSR. Don't worry about this. This is just nonsense. This is memory addresses that we care about. But this is just basically saying, oh, the parent of this environment is the environment of this package. And if I ask for the parent of this guy, you're going to get the stats package. So we can chain these guys together. We can even type correctly. And there we go. That's the stats package. Okay, so now that it's gone off the screen, okay, it's chained up here. That's a general rule in R. How does R find something? Given an environment, it's going to, given a starting environment, it's going to start here and then look through its parents, all the way through the ancestors until it finds it. And ultimately, it's going to go through different paths in different circumstances, and ultimately, it's always going to end up at base, the base package, where the plus is defined and the minus, because you can't really go very far without the mathematical and logical operators, okay? But that's the way things are going to work here. So why do we care about this? Because when you get to understanding why a function in an R package doesn't behave itself, you better figure out where it's seeing its variables, okay, and where it's finding them, and it has a complicated method, okay, but it's always actually a simple method. It's just chain the parents together and go through. You were about to say something?
I was just wondering, does it do an exhaustive search through everything in the environment for a name, or once it finds an instance of that name, it will end the search?
So when it gets here, if it can't find pi, it goes on. If pi was in here, it would find pi and immediately return and terminate the search.
But what if there's a duplicate name?
It finds the first one. Now that's a good thing. And a really bad thing, okay? Because now the order of your search path, if you have two packages and they both provide a function called plot, okay, and I always forget that really when I come across ones where you go, no, that makes perfect sense that you would actually have two names that are really similar doing radically different things. But now if you run a command here, at the top level command, and you run it, but you got these packages loaded in different order, or I have package A and you have package B, we're in trouble. We're getting totally different answers. And you go, look, no, my answer is 4. And I say, no, my answer is a long vector. You know, you go, like, I have no idea. So this really, really matters, okay? Now, there's one other thing which I'll just throw in. I'm going in sort of a slightly random order, you know, but not entirely random. And this is all in my notes. It is very smart. If it knows it's looking for a function and it finds the name here, but it's not a function, but it's a vector or a number, it keeps moving on. It sometimes knows from the context, I am looking for something of this type, in which case it will continue on. Even though the symbol is there, we know that the value is wrong. Okay, and that's only for functions, although we can do it manually for other things. But the evaluator does that for functions. But this order of the search path is a nightmare, okay? So, and also there's another thing that you can think about. If that search path becomes, so CRAN, the Central Repository for Archive Network, okay, where many of the R packages are, has about 10,000 packages. You can load them all up. Okay, you can have them all on your search path. Hey, you never know what I might use. First of all, the order will be nuts because you won't know which one you're getting. But secondly of all, it's going to take forever to search through them all to get to base. So if you're looking for plus, and it's not in any of the 10,000, and it shouldn't be, it's just going to be nuts. Okay, so you want to keep the search path as small as possible. Okay. So, and it's very convenient to use, if I'm constantly going to GR devices and using the PDF function there, and the PNG and all these different things, let's just say, I don't want to have to say GR devices : PDF. It's just, you know, I want to type quickly, okay? But if I'm only going to use it once or twice, it might be worthwhile to actually spell it out fully and avoid having it on the search path. It reduces how much searching we're doing, and it also just makes it much less ambiguous that there's not a PDF function somewhere else. Okay? Any other questions? You have a question, sorry.
What determines the order that they determine?
You determine the order. Okay, or not, unless you. But when you type library, so let's just take. Okay, so let's just type live. So let's just take a look at the search path. These are great questions. I forget what's not obvious. So please just yell. Okay, I did actually write this down in the notes. Thank you. I was going to. So this is my search path now. Let us load. The package, by the way, we have this horrible terminology from legacy. We use the library function to load a package. The individual packages are packages. They're not libraries. They could be libraries of functions, but we have libraries of books. Okay, each book contains things. Anyway, it's just an oddity. But if I now load stats 4, let's say, okay, so now that's fine. That's a package. Okay, now let's take a search. Now let's look at this. There we go. It's now inserted itself into position number 2, which is the default. If you take a look at the library function, the second argument to that is a thing called pause for position, and it defaults to 2, and we'll talk about how all that stuff, how you would read that. But basically it says, I will attach it in position number 2. But if I wanted to, I can easily do the following. So let's do our part, because I happen to remember that's one that's built in. So let's just say now, I will put this in at position number 10. Okay, and now take a look at my search path. Okay, and where did our part go? Did it? Hang on a second. Where did it? It's still in 2. Did I hang? Maybe I'm. Thank you. Now I need to find another one. Let's just. Okay, let's just do this one, and we'll say pause equals this guy, and. Okay, and now this. So it's not the second argument. Sorry, I can't remember what it was. Okay, but there's a pause argument. Okay, for position, and now this read PDF package has gone in there. So I can control the order of all of this stuff, and I can remove things and add them later on. And so I can shuffle this all around. Okay, and that's no problem. Okay, happy? But it's an important thing to know that you may be getting the wrong function. Okay, so you should be in control of this. And again, a lot of this, I'm thinking, when things go wrong, you need to be able to reason about why things go wrong. So am I finding that the right thing on the search path is a good one? Yes.
I'm a little lost in why the order of these packages matters.
Okay, excellent. Thank you. Okay, it's because Because when I'm looking for the, what will turn out to be, well, when I'm looking for pi, okay, because I want to execute the command pi, so, you know, which is just, here's the name of a variable, go find it for me, which is what I'm telling the evaluator. What the evaluator does at this top level command is it searches through this search path. Okay, that's why the order matters, because it stops when it finds the first one that is appropriate. Okay, does that answer your question?
Yeah.
Good. And this is when you're in two modes when you're working with R. Okay, you'll be writing functions. Okay, calling up, okay, and doing all sorts of stuff. That comes second. When you're sitting here just issuing commands one at a time, this search path is your entire world. Okay, because that's where things are getting searched on. Okay, by definition, or, you know, through its name, it's a search path. We're looking for for variables, and well, and we have to explain what some variables are and we're not. You had a question?
Yeah. So the little semicolons means you don't need to load with library.
No, you do not need to. No.
Require is the other thing that you see, like, a lot of the times require they use.
Sure. Okay. So good question. Okay. So first of all, when I just did something like the following, so if I just go in and say XML, that's a package that is not on the search path. Yes, we're all agreed. And if I go in and say, okay, give me the function XML parse, it says there it is, and it prints it. Okay. Okay. So, and if I go and take a look, so that's okay. So let me just kill this off. Now let me just go and, is XML on my search path? It wasn't on my search path. It still isn't on my search path. This double colon operator says go into the package and get out that symbol. Okay, so here's the name of the package. Here is the name of the symbol I want, and R goes off. And exactly what I hope I explained to you was when the evaluator sees this, it's parsed it. It knows what to do, and it goes off and finds the symbol. We've told it in where to look specifically. It goes in, grabs the value of the symbol, and returns that. That's the result of evaluating the symbol. Okay, so that's the double colon operator. Okay, and it allows us to not use the search path, which is much. It means we're not building the search path up to be huge, okay? As well as it's a little less convenient to type if I'm typing this 100 times, okay? But it also avoids the ambiguity of finding another function named XML parse. As to the other question about require, library and require are the same thing with only one essential difference. The library function loads the package, and so does the require function. However, the library package will fail if the package can't be loaded, if it's not installed, or if it just is installed incorrectly. Whereas the require function will actually fail to load the package and return false. So this is often something we want to use, which says, try to load this. If not, I'm going to do something different. Okay, then I'll go off and install it myself or something like that, or I'll use a different package. So require is a way of not getting an error. Okay, but their library and require are exactly the same. Adam.
So is double colon that the scope resolution?
Speak into the microphone if I
Sorry. Is that the equivalent of scope resolution operator?
And this is it's not really scope so much, because I think of scope as how it finds things as it goes off on its own. What path will it take? Whereas we're being very specific about what to actually where to look. So this is actually saying here it's essentially a namespace extraction function. In addition to now, there is a third thing. Again, this is not the order you would. I'm assuming that you know your way around enough to at least ask questions about this. Sometimes you will see 3 colons. So for example, I do this. There's a function called trim in there, and it goes, go away, you're an idiot. Okay? Now this is not a syntax error. This is an evaluation error. It parsed this correctly, but it says, I cannot find that symbol. You must be wrong. I'm not wrong. It's in there. It's just, and for once, it actually gives an error message that is actually not entirely incorrect, okay, or misleading. Okay, it says it's not in the exported namespace. So sometimes sometimes you will use this, although not a good idea. Okay, and it's 3 of them. 3 colons in a row actually says, yeah, trust me, I'm going in behind the scenes and pulling out the variable that I know is there. Rarely use that. Don't use that. Okay, but it is there. I'm just giving you for completeness. Everyone happy? Any other questions? Yep.
You mentioned the difference between library and require. I'm just curious, can you give an example of when you would want to use require?
So I might say, and I could go find one. I could find an example soon. But I'm basically saying, if require this package is false, okay, then go off and do something else. Okay, so I'm going to use a different computational approach. For example, if the SVG graphics device, you load up the SVG Cairo graphics device. If that fails, okay, then I'm going to just use a regular PDF. Okay, that sort of thing. Or I might say, if I can't load it, if not require of this package, install that package of that thing now, and then library of that thing, and off we go. Okay, but so they're the two basic high-level ideas. Yeah. Okay. By the way, all we've done is evaluate literals and variables at this point. Okay, I've shown you how to actually compute the answer 3 for 1 plus 2, but I haven't told you how it works. But I have. So what does 1 plus 2 do? Gives us 3. It reads this in, it parses it. So let's just parse it for fun. Okay, you will never have to do this because that's what the top level interface is for. Let's just, okay, let's just do this. That's E. What's the class of E? It's an expression again. What's E? There it is. I'm going to say, let's go in and grab the first one. There it is. So far, so good. What is that? Remember, pi was a name. Remember when we parsed pi? It was a name. When we parsed 1, it was a numeric. What is this guy? Character? If it was a character, for those of you who've lived with R for too long, no, it wouldn't be, because we'd have to have quotes around it, because that's the way R prints characters. But good guess, because we're guessing at this point unless you actually know. Okay? It's a weird thing that you see all the time, and you will actually use them in some program, in some functions. You actually manipulate these yourself. Okay? It's a call. So basically, what have I said? Okay, we got this read, eval, print loop. It's important to understand how the parser works a little bit, but more to the point, the evaluator. And we've got environments. Environments are the heart of this thing for finding variables. Okay, and this call thing is everything. Okay, I kid you not, because this is an example. I kid you not that everything that isn't a literal or a symbol, and 1 or 2 other things that I can't remember, okay, but are very rare. Everything in R is a function call. And that's why it's so simple, okay? Because if you master that, you're done. And it's not trivial. Function calls are very rich, but there's still only 2 or 3 things you need to know about them, and then you're done, and then that is R, okay? Because everything is a call, okay? What are we calling here? This is expression. No, the expression contains the call. So what are we calling here? So I do this for a living. I pull these apart. Okay, but if I do the following, if I do E of 1, okay, that's just the call. And if I look at the very first element in it, it is 1. Is it? I'm not looking, but I know it's not. You think it'd be 1, and it's really annoying because you think it'd be 1, but it's not. Oh, it's an error. Okay, but it's okay. It's where are we going here? Okay, so that was a syntax error I got, because you see I had missing a square bracket here. That's not a semantic error. That's not runtime. The evaluator hasn't gotten here. That's a parsing error. It's broke, and okay, so if we do this, and what does it actually give us? It's the plus. Okay, so what this actually is plus with 2 arguments, 1 and 2. Okay, so for those of you who like reverse Polish notation and all that stuff, it's just the way God meant it to be. Okay, but when I do something like plot x comma y, it's obvious that we're calling plot with 2 arguments, x and y. It's exactly the same thing. What we've done, what R does, is it takes this ridiculous syntax for plus, adding 2 numbers and putting them on the left and the right-hand side, and just turns it into a call to plus. okay, with these two arguments. And same with minus and the multiplication. It's the same thing with the logical operators. It's the same thing even with this. If I do the following, 1 through 10, okay, e is equal to that, e of 1 and 1 of that guy, that's the colon operator. So this is all syntactic sugar to get back to the one uniform thing that happens in R, which is everything is a function call, okay? And that makes our life a lot easier, okay? Yours and mine. Now we only have to implement function calls, okay? And it also makes yours simpler because you only have to learn one thing. And that's, I like languages where there's very little to remember in special cases and all that sort of stuff. You just want one single sort of computational model. Anyway, so that's what's actually happening. So let's go back to 1 plus 2. So now you actually know what's going on. What happens here? What does this parses? You've seen what it parses to. It's a call to plus with 2 arguments, 1 and 2. What does the evaluator do?
Calls that function, returns the value.
It does, but what function? So what does it do first? It has to go find it. Okay, so it starts in the global environment and looks for plus, and it wanders its way down and it finds it in base. Now that it finds it, it's got it, and now it can actually call that function. And we all know what it does. It hands off 1 and 2 to the thing. And in fact, so we can. So just remember what I did with this. Where I sort of said XML parse. I could just print this. This is the read eval print loop. It's printing the result. Because I didn't assign the value to anything, R just prints it. If you assign the value, if you assign a value to a variable at the top level, R won't print the result. It says, okay, just store it away. But here I haven't actually assigned it, that's fine. So if I'm right, if I haven't been lying to you, I can tell we should be able to see the plus function because it's in base. Because it's not built into the language, okay? It just doesn't magically disappear in the parse tree, okay? It's plus. So we can just, I showed you we can see the XML parse by just printing it, so I'll just do this. What's happening?
Inside the function, but it's not returning.
It's inside the function, but it's not returning? Nope. No, I can tell you that can't be true. It can't have already entered the function because we haven't called it yet. Because the critical thing to make a call to a function, because we can refer to functions just like I did with the XML parse. We can refer to them. I don't care if it's a function. I just want to see it, or I want to do something with it. Okay. But so if I do, here's my function f. If I just type f, it goes on, finds the symbol. It searches through the search path and gets the value of f and shows it to me, or I can do something. I can hand it to another function. But once I do this, okay, if I just do this, the parser, if I just stop now, the parser will tell me I'm an idiot, that doesn't make syntactic sense. It's not a legal command that I'm going to bother the evaluator with at all, okay? The parser stops here and says that's an error. But once I do this, okay, now it's a legitimate command, so the parser hands it off to the evaluator, and the evaluator says, I'm looking for a function named f. Okay, and then I'm going to call it. Okay, so it's 2 steps. But now I have to go find it. But I never put the parentheses in here. So I haven't even found the function. So why is it stuck here? This is particularly insidious because I've got a plus and I got a plus here. And they're totally different. The second plus is a continuation. It says, oh, you'd like to break your command up across 2 lines. Well, then I will be kind enough not to say, here's another prompt, here's another greater than, because you wouldn't have any clue that I'm waiting for a completion of the command. So it just says, by default, the continuation prompt is plus, which is terribly annoying. It's almost like I picked this one on purpose. Okay, because it's like, this is really annoying. Like now it's just starting to echo what I say. Okay, because look, I can do it again, you know. Okay, there you go. It's like, oh, okay, now if I don't understand what's going on, I'm confused. Okay, so you just close your laptop and go home for the day and start over again. Okay, but there is actually some point to this. Okay, that plus, see what's actually happening is that's a perfectly legitimate command. Okay, see if I just do this, it won't like this because I just put the okay. Well, okay, it's happy enough. Okay, now it's just +1. Okay, because that's right. I can easily just say +1 or -1 if I wanted to, as a unary operator, just minus of a literal value. So that's a perfectly legitimate partial command. But it wasn't what I wanted. I wanted to say go get plus. So how do I tell it to go get plus?
Find plus.
Find plus. I can say find plus, but that doesn't get it, by the way. Find and get are different. I say find, it tells me where it is. Get goes and gets it, but then I have to tell it where to get it, which I can do. So I can use find and get to do this. Yep. So there's a function called get, which is implicitly in the evaluator. You rarely have to call a get yourself. Backticks. Okay, because my problem is I need to tell the parser, don't treat this as the plus. Treat it as the name of a symbol, okay, or the name of a variable. So we can use this if we wanted to. Okay, backticks. Okay, this is just a special thing. It's very handy for actually going in and grabbing things that are special keywords, okay, or complicated things. There we go. That is the function. That has gone and found it. What I've asked it now to do is, that if I parse this, that's a name. So now the evaluator goes off and looks for the variable with that name and then grabs the value and returns it. In this case, it returns it. It's a function, takes 2 arguments, and don't worry about this. At some point, we actually have to implement arithmetic. Okay, it can't be turtles all the way down. Okay, so that's fine. So we can now find this. So this backtick is fine. Remember, I told you everything is a function. I told you plus and colon was a function. What are things that can't be functions in any language? You know, plot's a function, sine is a function. You know, LM for linear models are functions, but there's other things in a language, not the vocabulary that and the functions you build. What are the things that we tend to use? You don't tend to use them up here at the top level command line, but when you're programming. What about things like for loops, if statements, or while loops, control flow? So I kind of lied to you, didn't I? That everything's a function call. I didn't. If statements are functions. While is a function. For is a function. Okay? If I type in while, oh crap, we're back to this thing again. Okay? It thinks that's a special word and it's waiting for my thing. But if I type in this, while is a function, and you can redefine it. And you can redefine if to do the opposite of what if does, if you so desire. Okay? Everything is a function. Okay? Not necessarily usefully, but I have seen people override if statements. But you can redefine all of these functions if you want. But anyway, everything is a function. Okay? Everyone happy? Yep.
When you have this primitive, does it mean that it comes from the early system?
Okay, so when we have a primitive like this, what happens? So when we look at a function, this is a very simple function. This is a keyword function that says, and here are the arguments it takes, and we'll talk more about this soon. And then this is the body of the function. This is very simple. It's only one line. Oftentimes there's many lines, as we saw. But this call to dot primitive, basically, it's not so much the operating system that provides this, but this dot primitive actually leaps down into C code that implements the R language, okay? And we have a bunch of these primitives that sort of know how to do certain things. Arithmetic, yep. Oh, and then we use the operating system for that. But there's other things that we have primitives for that we actually need to go down into C code. At the end of the day, R is an interpreted language, okay, and that's one of the reasons it's slow. It uses this evaluation mechanism of even looking up plus and minus for every single operation that it does, but eventually it does get down into some C code that actually makes it go fast enough.
So I was trying to think through how would I pull some of these things apart if I was like trying to learn this on my own. So when you were looking at E, and you were using 2 sets of square brackets, I'm like, okay, well, you're going into the first part of that, and you're going into the first part of that other thing.
Yep.
So I looked at the structure of just E and the first set of square brackets, and it returned language 1 plus 2. So my big question is just kind of like, these don't seem like objects that I normally
No, and you don't.
How would I have known that plus was actually the first thing? They're not lists.
They are special things, and we don't tell people about them. These are language objects, and you do actually use them. We use them for different things. Again, not many people use them. This is definitely advanced stuff. Okay, what we're doing here today is we're straddling elementary R. And it is elementary R that tends not to be taught, but it's also very close to advanced R. There's, it's everyone should know this stuff, because you're driving a machine that if you don't understand how it works, you're just hoping it gives you the right answer. And you can, there's a very good graduate student who wrote a nice book on bioinformatics with a large chapter on R, and he knows an awful lot of stuff. And he mailed me about 6 months ago, going, I just lost 2 weeks of my life because of the tidyverse, because it has non-standard evaluation doing something very odd, and he really knows what he's doing. And yes, not fully understanding the computational model means you can really get the subtly wrong answer. And this is a problem. But this stuff is way too advanced for most people to use. But if you take a look at the plot function, the way we put labels, when you say plot of MPG against, we put that label on. Okay, how do we know? The plot function doesn't know what arguments were passed to it. Well, R does know. Okay, the plot function does know, and what it actually does is it actually goes and grabs this call and then starts tearing apart different pieces. Okay, so they can be very useful for actually enhancing your functions and doing interesting things. How do you learn about them? There's a couple of places. They're documented in the R manuals. Hadley Wickham has an advanced R book, and they're in a few other places as to what their structure is. But basically, they have. Remember, I said everything is a call. So now every call just looks like here's the thing that is being called. And then the other elements are the arguments in the order they were provided. Sometimes they will have names. Sometimes they will not have names. Okay, and that's in essence what they are.
Yeah. So why is the colon the first thing in that?
Because this is just merely syntactic sugar. Okay, because it's really a call to colon, which takes two arguments, 1 and 2. Okay, 1 and 10 in this case. So the first two arguments. So everything. What the parser is doing is turning all of these weird syntaxes back into the regular uniform call. Okay, and that to me is just a piece of magic. If you understand that, you can reason about everything. Okay, because it's now everything's a call. Okay, and that's why I'm emphasizing this so much. Okay, you had a question.
Are all R packages written in C?
Are all R packages written in C? No. A few to some extent. A small proportion are written in C. No, almost all of the functionality that you need is already in the R engine. So ideally, and I genuinely mean this from the bottom of my heart, you avoid C like the plague, okay, for two reasons. One is it's hard, and it's very error prone, and B is we can't actually do as much with your code as if you just leave it in R. That's a bigger issue, but for the most part, I would say today probably, I'm making this number up, but approximately 70% would be pure R function, all R code. There's a lot of people who need speed, and they write in C and C++ code, and a lot of people are using the RCPP package. But one of the problems with this is that it becomes we can't put that code on in parallel, sort of an automated for you. So some of us are working on making stuff very faster in R, and that code is essentially a black box. But no, for the most part, you do not need to write in C and C++. One of the reasons people like Python and R is because you're not writing in C and C++, because it's way more productive use of your time, not of the computer's time. There's a penalty for R. If you think about what we just did, okay, we added 1 plus 2, and I told you that R had to parse this, keep the 1 and the 2 around, and then had to go find the plus by looking through the entire search path, okay? Now looking through that is a lot of code to actually, a lot of commands to actually say, are you in there? No. Okay, move on to the next guy. Moving on to the next guy is code, actually CPU instructions, okay? If you consider what's going on there, and when you consider what a C compiler will do that, it will actually compute the number 3 before it actually even compiles the executable code. It will just give you the answer back immediately. So there's a huge overhead between C sort of, well, obviously R up here and C down here. But there's a factor of at least 300. Okay, speed up difference. But a lot of code goes back to R's C code, in which case you don't pay that penalty. But now you're writing in nice high-level R functions, where one line of R code does thousands and thousands of CPU instructions, whereas one line of C code may be doing, you know, only sort of 10 or 15 or 100. And, you know, and anyone who's played with C long enough to blow their head off and sort of just sit there for weeks going, I don't know why it doesn't work. It says it's working. So they're much better language. These are much higher level languages, and we only drop down to the low level C code when we absolutely have to. I gave a little workshop here on making R code efficient in pure R, not going to C. Just there are certain things you could do to make it go faster by avoiding certain things. Okay, so always try to make your R code faster and faster and faster until eventually you need the performance gain. Then my simple answer to that is get more computing power. You know, get more RAM, get more computers, and run in parallel, and life is good. And then eventually, when you have to, okay, I will do it. I will write C code. Okay, but I have a student who just gave a talk. We are working on this thing, which is kind of, it's far from being general purpose, but one of the nice examples we have is we wrote a random walk the most stupid, naive way you do it in R. Somebody else, we wrote it the fast way using a lot of R clever techniques. We got a factor of 300 speed up. So the clever R and the dumb R are a 300 times difference. Okay. We ran the dumb version of R and outperformed the really smart version of R. Okay. So even doing dumb stuff can still work really well in certain cases. That's what we're aspiring to. So don't go writing C code for fun, because it ain't fun. And if you want to graduate in the next 5-6 years, just stay away from C. Okay. So everyone happy? So I actually had. So here's I put up some questions. We don't have to do them. But is this a legitimate command?
Yeah.
You only have 50-50 chance. Why? Okay, so the parser actually sees this. We saw this plus waiting for everything. So this is perfectly fine. So is this. Is this? Okay, because this is not a unary operator. Okay, so the parser now just folds over before it gets, and we don't make. Unfortunately, we should. We don't sort of say this is a syntactic error. This is a runtime error. But it's important to know. Is this a legitimate command? Who said yes?
Yeah.
No, it's not. This is really, really annoying. This is, you spend hours looking at this, like, wait, where is that? This is where syntax highlighting can really, really help. Is this a legitimate command?
Probably no. You need double quotes.
If I put double quotes here, then this quote is fine. R has this thing. I'll take quotes in either form, single quote or double quote. But by God, you better end with the same one. Okay, they have to come in matching pairs. So this is very handy. I put a double quote here, and I don't need to do anything with this. But otherwise, I have to escape this, and I put a slash in to say, by the way, don't treat the next character as actually what you think it means. Just treat it as escaped. And likewise, this is bad news. But if I put single quotes here, this is fine. There's two things. The parser will tell you this. The parser will say, I can't parse this. This is nuts. Okay? But also, in any good interface that you're using, this should be color-coded. And you should see this bit changing color. And you go, hang on, what's going on there? So color, good syntax highlighting is important. How do we get the print function? How do we get and print the plus function? I think this is the backticks guy, okay? Because it's part of the language, R is sitting there waiting for you to do something else, and we said, no, we need something slightly different. Here's a little thing, okay? I'm doing your exercises for you, okay? This is again for nerdy people like me who actually like looking at language details. What's going on here? Let's just parse this guy. Now that we have the parse function, one of the reasons I don't think you're going to need the parse function very often. Okay, but it doesn't hurt you to know about it, but it helps you to think about it and to reason about it. But one of the things I'd like you to be able to do is you can play with this language. You can actually just go in and say, what does it think it is doing? Okay, what have we got here? This is actually, if you look at this, this is slightly different from the one we've seen before. It's got two things. What's the first one? T, and what's the second one? Okay, what is the class of this? Logical. What is the class of this? Pardon? Name. It's not a string because it's just a symbol. That tells you something very, very important. And I see a lot of people doing this, and we tell people don't do this, and we know why they do it. I do it myself. I actually almost never do this. Okay. When our this is of class logical. Okay, so just to be explicit, what are the class of these guys? It's a name. This is the T, and this is the logical, which is capital TRUE. That true was the parser recognized that as a literal value, just like 1. It said that, oh, that's true. That's actually the built-in logical value true. This one is a name. So when we go and evaluate the first one, it has to go off and find T. Okay, so it looks along the search path. Okay, everyone with me? So let's do a simulation. And we'll start at time 0. Now, what's T? Is it true or false? So just by misusing T for another purpose, I will now kill your code that uses T's, capital T's, as a name. It's a variable, and we're allowed to change it because it's a name. The name says this is a variable, it's a symbol. This is a literal. You can't change a literal. Here, make 1, 2. No, I can't do that. Okay, so this is an illustration of how you can actually go and figure out what the computational model is to say why capital T is a very bad idea to use for equivalent of true. Okay, people do it all the time. Okay, and occasionally they sit there for weeks trying to figure out what on earth is going wrong with their code, and then they go, oh, and what's worse is they send it to me, and I go, works for me, and I go, well, no, okay, try it again, and you do this, and eventually, you don't have capital T set in your global environment, do you? Oh yeah, I do. And then, you know, if you're lucky, it's set to T is you start your simulation to time equals 1, okay? But F, for example, F, good variable name for an F test. Let's take the value from my F statistic and assign it to F, which is never going to be 0 by definition, okay? So you're in trouble. Okay, so we don't use T and F. And then just, so here is a command we're going to actually look at later on. If you want to understand what's going on here, you can parse this, and actually you'll see that it's another one of these calls. Here's the thing it's calling, that's the first element. Here's the second element. This itself is a call. This is a recursive hierarchical tree, okay? But you can go in and play around with this stuff. Some of us, what we actually do is we go around and we actually change them. We grab the call, we change things, and then we evaluate that. So we actually say, oh, we're going to do almost what you're doing, but we're going to play a different game, which is kind of mean, okay? Because you don't know what we're going to do without reading our code. And how many of you use the tidyverse? That's what's going on, okay? It grabs the calls and changes them, okay? And you need to understand it's a different computational model, okay? What I'm describing here is R's computational model. We go look stuff up. We haven't actually got to how you call a function, although we implicitly call the function, it's been obvious. But when you actually use non-standard evaluation, you now got a different computational model creeping in, so you got to remember 2 different computational models, okay? And you got to know the interface between them, which is all well and good. It's all great, but it is a cognitive overload for many people when things go wrong. It's great when it works. It's a nightmare when it goes wrong. I program in multiple languages simultaneously, and oh my God, I was just doing something where I was just saying, that's perfectly, oh, that's C code. Sorry, I'm not allowed to actually write that in R. And just, you get different things just because your brain doesn't actually transition very well. Okay, any questions at the moment? So this is what we've, any questions? Sorry, somebody? Yeah, good.
it's pretty elementary.
That's fine. That's
Can
good.
you just go over the difference between character and name as a class? Is character just the umbrella that name falls under?
No. A character, so it's easier to go between one and the other. Okay, I can turn a character into a name and a name into a character. Okay, and for the most part, you don't care. You're never going to see names, except for the one case I'll show you if you want. For the most part, you don't care about names. The reason I'm showing you them is because they are at the heart of how we actually evaluate things. Okay, and that's why when we were when R sees this, it has to go and it says plot. I need to look up plot, and I need to look up X. But here, this is actually if I typed it correctly, okay, this would be a string. And that helps. That means that the R evaluator knows the difference. It says, oh, that's a literal value. It's a string. But this other one has a context. It's being used as a variable name. And so a name is being used for identifying a variable. Does that answer your question? Okay. So as I say, you can easily switch between the two of them, but names come from calls, and they're typically referred to symbols. But so the parser will put this as a name, this as a name. Okay. And it will put this as a literal character string, and because it's already done the computation. If you want to think here, the parser knows that this is the ultimate value of this. It's a literal string. Whereas here it says, oh no, you're going to have to go and find the value associated with this name. Yep.
So I suppose I have a follow-up then. How did, when we parsed the text T semicolon true, how did R recognize T as a name and not a character value?
Oh, because there was no quotes around it. Okay, so let's do that. Let's do this. Good question. Okay, very good question. Let's again. So I'm going to put a capital now. See, so now let's do this. So what's the length of E? It should be 3 now. And now we go back and do our sapply. Now we got a character, a name, because there's nothing here. Now, again, we've parsed this. We haven't said go find T. We haven't handed it to the evaluator. So T doesn't exist, okay, necessarily. But this says this is a character. This is a literal character string. This is a name that you're going to have to go find, and this is a literal logical. Happy?
Yes.
Good. It's somewhat subtle because you don't normally see these things. You don't see names in the wild, okay. But if I let me just. But just for fun, okay, this is how R knows what the name of the variable was in the call to plot. So it can put it on the X label axis and the Y label axis, okay? And what's it doing? Forget about the dparse. It's the substitute. The result of substitute of X is your first argument. And I'll just leap ahead just because I think the more I say this, the more times I say it early, and then we come back to it. You'd think X is a value, but it's not. It hasn't been evaluated yet. This is a thing called lazy evaluation. So when we say, hey, substitute X, it actually goes and grabs the command that would yield the value of X, and it gives us the call. It could be a name, or it could be an actual call, and then we can and now we have that. And then, so we have the call, and now we can screw around with it and take out the first element, do things. Or we can just turn it into text and use that as a label. Okay, so so sometimes you do see these calls in the wild. Okay, for the most part, you just need to call substitute and say, okay, I got my thing. This is a very common idiom, dparse substitute, which says just give me the text representing the code that was used to get here. Okay, but this is where you can actually see the calls in the wild. Happy? Am I scared?
For the third example on exercises 1.
I just keep moving away and you sorry, this one?
Why doesn't the parter read the third one?
Of these 3?
Mm-hmm. Why doesn't it read one next line times 2?
Because
plus usually if it's
because
on the first one, I imagine go 1. The first plus would be treated as the next line, then it would read plus 2.
This plus would be the next line?
Why does it not?
So so I'm not sure. Everyone's expectations about how R works are perfectly legitimate. We could have programmed it any way we wanted. There are when we design languages, we go for uniformity and simplicity and blah blah blah. So here's a conjecture that I think. Why would the plus mean the next line? Is that because of the continuation prompt we had earlier? No, because that's something that R spits out. That's not part of the input. Okay, so when we write plus, we don't mean, oh, and continue on to the next line. If we meant continue on to the next line, we would hit return. And it would have automatically put out that plus prompt. Okay, but for us, we're saying 1 plus, and it says, okay, now there's another operator coming, and then it sees this, and it sees star, and it goes, okay, I hope they're going to put a parenthesis here, okay, because then that could be a function call. Okay, even that won't work, we need backticks, but okay. But now it says, oh, that doesn't make any sense, I give up. Okay, so this plus is not the continuation line, it is the operator, the arithmetic operator. Happy? Would it make any? Would it help if I changed that prompt from being a plus to being give me some more? You know, and which we can just basically say, you know, in the options you sort of say here are the prompts, okay, and yeah, we can put in whatever you want to do. It's like, come on, you know, I'm waiting, you know, and then the plus it wouldn't be as we wouldn't be aliasing this plus. So this plus means very different things, and that's one of the problems. These things mean different. We have how many symbols on the keyboard, and we use them in many different contexts in different ways, and that's what I mean about the reasoning behind this language. This is just in the parser, but just how do I reason about what makes sense? And that's what you're saying is perfectly legitimate. We could use that as a continuation marker because we did in the R interface, but in other cases. Sometimes we're typing R commands and they're too long, so we hit return and then it asks us to continue. In most cases, and I encourage you, what you're actually doing is you're writing R code in files and you're just sending them off to R, in which case it may actually just suck up the entire file in one go, or you know, it knows which bits to actually which bits to send, and the parser isn't doing what we're doing here. Okay? Any other questions? So I hope this hasn't been too obscure. To me, this is actually fundamental. And it's really bare bones stuff. It sounds like, I don't need to learn this stuff, but I suspect most of you learned something that you hadn't seen before. For the most part, the fact that everything is a function call is weird. Okay? You know, I was just showing Clark something, you know, this is something that's weird. In most programming languages, when you do this, you say if something like this, x equals 1, else x equals 2. Well, just do it that way. That's weird. If is a function, and it returns a value. What value? Whichever one of these it executed will be the last. And if there's multiple lines in here, it'll return the last value evaluated and assign it here. This is weird, okay? So that fact that everything is a function is weird. I kid you. If you
it's not going to return assign x to like true or false. If the condition is true, it's not like.
No, it evaluates this, then it evaluates one of these two, and whatever the last thing to be evaluated was will be the value of x at the end of this. If you do this, don't. You can, but don't. Don't ever do that, okay? But everything is a function call. That's weird, okay? But as I say, it really does mean that now I only need to teach you one thing, and that is how do function calls work, okay? And then we're done. Ha. Not quite, but close enough, okay? Yes?
I didn't say that will not use that.
The for, never assign a value from for. First of all, don't use for loops. Use an lapply, sapply, vapply, all these different ones. If you need a for loop, create the value, you know, assign the values as you go along. For some reason, I believe, if I'm not mistaken, I can't remember now, but it may actually return the last value of I. I can't remember what it actually returns. Which a factor? No, it just basically, if I remember correctly, it returns the wrong thing that you're expecting. You want the last value and it doesn't. Anyway, this I actually do use because it's very clear. If I got 4 lines here and 4 lines here, it says I'm still setting x. It's much easier to read because otherwise I go like, what the hell are they doing in here? Oh, you know, they go now, oh, look, they both set x at the end. Okay, I have to untangle that. This is easier to read. This one is nuts. Okay. That's what it's either it returns a null or returns I. I can't remember which one it is. I think well, in your example, of course, it could be different with a different example, you know. But yeah, I believe that something in my mind rings a bell. It's null, but another one, it could be the last value of I. But I think
even if you inside the prerequisites put in I, it's still returning null.
yeah. So basically, don't ever do it. It's nobody in their right mind should actually use the result of a for loop to get to as the value of the for loop. It's just but the if statement is very useful. Okay, so this is what we talked about. The REPL, how this evaluation works. These are totally different. We also talked about just literal values. That was good. Everything's a function call. Nobody has any questions about environments? How many of you have seen environments before today? Okay, you all have. Every single one of you have seen environments because you work on them every single day. And the ls command and the ls parentheses all equals true to show up the ones with the dots and so forth. All of these good. This search path, how many, did you know about the chaining of these environments? Okay, so this is actually helpful. Do keep that in mind, okay, because what we're going to do later on is we're going to actually get into the middle of a function and go, oh hell, something's gone wrong, and then we're going to actually we're going to walk up through this environment chain to see where it's going to find things. Okay, so why don't we take a 10-minute break, come back here on this clock at 25:02, and we'll continue on from there. Looking very stern. I teach this in different ways, so if this is not clear to people, or if you have any suggestions to make it clearer, please let me know. I'm more than willing to entertain those suggestions. Hopefully, as I say, hopefully this is of value to you guys. Okay, the next piece of this is on Thursday. My plan is to talk about the data structures in R. They're very simple. But there's a couple of interesting ways aspects to think about, especially subsetting. I was just writing up, I was writing up some stuff yesterday. Subsetting with matrices gets really entertaining, but very, very powerful. There's hopefully I think I put it up. There should be, if not, I put this all up very quickly this morning. It probably, all the stuff is there, but you can't see it. So I have to put links. I have to put links in for this. There's no links here. I have notes on all of these different things, which basically go through what I'm saying. Please remind me to put them up very soon afterwards, so that you can see them. They are there. So again, environments really, really important. We'll see a little bit more of them, but they are very, very simple. They're just name value pairs. Okay. They have this weird difference than almost all our objects in that they are mutable. Okay, so they're not passed by value, they're passed by reference. If you actually are messing around with environments, most people aren't, so that's okay. The next step along our understanding of R is calling functions. Okay, we saw how to call a function. We sort of, you do 1 + 2, and that turns into plus parentheses 1, 2, okay, or any other function. When we have real functions where, plot of x, y, you just pass in arguments. It's all blatantly straightforward. Everyone knows how to do it. It all just magically works until it doesn't. Okay, and then you go like, why did it do it? So I have okay, and that's all to do with, so what we said was, when R sees a call, the very first thing, and this helps me in my mind. I drew a picture of this, but I hate drawing pictures on the computer, so my tablet was dead, so I'll draw it here. So let's just go and take a quick look here, okay? So let's go back over to our example here. Yeah, let's take this example, okay? Okay, so this is a call. Okay, if I parse this, as I was encouraging you to do, and I really do, just go, you know, the nice thing about this is nice informal. There's no exercise. There's no homework quiz. When you're bored, you want to just distract yourself, and you still want to pretend you're working. Go in and actually just parse something in R and just screw around. Walk that list and see what's there. And go, why is that first? Why is the plus first and not second, and so forth? And see what you've got. Always within R, you can always say, what's the class of this? You know, what's the length of it? You can always ask those questions and interrogate it, and then see what you understand. But basically, we've got a call here. We've actually got another call here. Where's the other call? Let me flesh this out a little bit. Just to, let me simplify this. This is maybe not the. I have different versions of this, and we'll talk about this. Okay, where are the calls in this command? Calls to functions. I'll give you a hint. This is not one. That's a literal. That's a literal. That's a literal. Literal. So everything else. So this is a call. That's a call. That's a call. There's one other call. No, that's a literal. That's in quotes. So that's a literal. That the parser will see this. And again, we can just parse this, and you can take a look. This is a call. And it will look like square bracket of empty cars and then nothing, and then a call to C. Okay, we can actually parse this and go in and take a look at it if you so desire. But there's lots of calls here. Okay, which is nice. Okay, so what does R do when it sees this? It's just. The parser has already parsed it. It now hands it to the evaluator at some point, okay? The evaluator looks at it and goes, that's a call, okay? It looks at the first element and says, scatter.smooth is the name, so now it starts searching along the hierarchy of environments, and it eventually finds scatter.smooth, unless that's not on the search path, in which case it just fails, okay? But once it's found it, then this is what it does, and this in my mind is, if I ever have to start thinking, okay, this is what I do conceptually in my mind. This here, this is what R does. It finds this. Okay, it finds the definition. It's now got it. I just printed it here. This is exactly when R has found and retrieved the value of this variable name. It is sitting with this definition. Okay, now. I don't know if you've ever actually done this, but that is an R object too. And you can manipulate it to death, okay? But, so if I do something like the following, which is scatter.smooth, again, you don't typically need to do this. I get back a list with all the names of what are called the formal arguments, or a better term is parameters, okay? They're not arguments. They're formal arguments, or they're parameters. I find it helpful to distinguish between the two. Parameters are what the names of the inputs that the author of the function used. The author of the function made up these names so they could use those names in the body of the function. These are parameter names. The arguments are the inputs from the caller. So there are two different people here. Okay? Okay, so the arguments are the inputs in this, when we actually have this call. This here, everything between here and here, these are arguments to this, in the call, in this one call to smooth, scatter.smooth. Down here, these are the parameters in the definition of the function. Okay, so what we've got to do is we've got to map these arguments to these parameters. And once we do that, then we can start thinking about the next step. So what we do, in my mind, is this. And there is something slightly funky we will get to in a second, but what I do is we draw a box, okay? And then we go through and we go through the parameters, x, y, span, degree, family, and I create a new variable here, x, y, span, family, okay, and evaluation, and so forth, and whatever else we have. Okay, XLab, YLab. What's the box? Pardon? It's an environment. Okay, it is one environment. It's part of the call stack. Okay, it's one element of the stack. This is an environment. Okay, why? Because I kind of said we create a variable for each of the parameters. That means, remember we said environments hold variables. Okay, and that's the only thing that really holds variables. Okay, so so this is an environment, which in this case it's actually a call frame. It corresponds to a particular call, one call to scatter.smooth. If I call scatter.smooth again, I'll do exactly the same thing. I'll create a different box. In fact, if I have a recursive function, one that calls itself, I'll have one for each call to itself, and they'll all be chained together, but that's fine, okay? What I do is I just create these variables, and what I do is I leave them essentially empty, okay? Then the next time, okay, so I have one for every single one of these. Then what I actually do is, and this is this is trivially tricky, if you will. It's just simple when you understand it, but it's I'm going to go through and see how this one has a default value of null, and this one has a default value of 2/3 and so forth. What I'm going to do is I'm going to go back and I'm going to actually say this guy has a default value of empty. Okay, I'm using this term, so we'll just call it the empty argument. Okay, this guy here has a default value of null, and this guy here has a default value of what, 2/3 and so forth. And so, okay. Now, I don't actually go in and assign those values. Okay, here's the trick. I go in and I assign for each of these guys what's called a promise. Basically, it's a promise to evaluate the default value. Okay? I'm not going to do it now. I'm going to do it later, when you need it. Because it'd be really stupid to go in and go, okay, let's call 2/3. Let's go and create this vector and all this stuff. I may never need it. If I specify the value for whatever it is, the family, why would I compute this first and then throw it away? Okay. So what we do is, and this actually, if this helps, great. If it doesn't, don't worry about it. What it actually does is it squirrels away the call. It actually has access to all these calls, so it just puts the call into the promise. Okay, and says, I know how to evaluate it. I'll come back later on and do it if you need it. Okay, so that's what happens. We create the step one, well, sorry, let's call it step 0. Step 0 is we create the box, the environment, for this one call to scatter.smooth, and then we just look at the definition and create variables for each of the parameters. Then we set up the promises to the default values. Now the next step is step 1. I say I have this written down in more detail, and I go through it laboriously and in great detail, so I hope. The next step is this. This is how R works for function calls. It says take every named argument. Okay, now we're looking at this. Take every named argument and go through and match it to one of the parameters. Not a named argument? No. Okay, these ones are actually skipping arguments. That's fine. Okay, this one is not a named argument, not a named. This is a named argument, and this is a named argument. Okay, let's go. Let's match L-pars. There we go. It matches exactly. And by the way, it has to match exactly. Okay? In this one case, it has to match exactly. Main. So what do we actually do over here? Okay, for L-pars, what we would do is we find L-pars over here. So now we're looking in the arguments. This is why I'm trying to make a distinction between the arguments and the parameters. We look in there, we find that this is for named arguments. Named arguments, and we're going to do what's called exact matching. Okay, it's exactly what I said. We go and look for, does this match any of those? But we're going to do 2 things. In step 2, we're going to do something slightly similar, but It's marginally different. This one matches perfectly, okay, to LPARS. So we have an LPARS over there. So what do I do? Now this guy already had, the default was what? Just to make a list. So this one here had, if you want to think about it, has a promise. It has a promise, and its contents was list. Okay? What am I going to do with this guy? This is the argument. This is the value of the argument for LPARS. What am I going to do? I'm actually going to replace this, and I'm going to put in list of LWD. Is that what I have? Yeah, LWD equals 2, col equals red. Now, this is important, okay? I'm not going to go and put in the list with these two elements. I'm going to put in the call to make that when I need it. Okay? Is that clear? And if it is, think again, because it's not. It's very subtle, and most languages don't have this, so most of the times you haven't seen it. We're not going to go and evaluate this call right now. We're going to wait until LPARS is needed in this function. I've called this from the top level. Okay? So in most languages, we just go ahead and evaluate all the arguments and then make the call, pass them all one down. What we're actually going to do is we're going to pass down essentially the code that will get the value of the argument if and only if it's needed. So we're still going to put it into the promise. Again, this is how we actually implement this. We use these things called promises. So this is now, here was the default value. It's been replaced by how to get the value. Okay, now let's go on. Let's match the next named argument, main. Where's it go? It doesn't match anything, so this should be an error. Except for ... That says, give me your great unwashed. I will take anything you want whatsoever. Just, I'll take it all in. Okay? So ... So we actually had ... down here. And basically now we add in the main equals this guy here, this literal, this string in this particular case. We add it to the promise. This ... is going to become a list. Okay? So we're going to treat it like a list. This, unfortunately, I cut and paste this for expedience. I have several other examples of this exact same function, and we should probably have started there. But let's just keep going here for the time being. Okay? So what I've done is I've now gone through and exhaustively matched all of the names, the named arguments. The next step is to go through and find all of the named arguments that did not match. How could that possibly be? Okay, because we said main goes in ... Okay, so let me just change this example very slightly. Okay, just to make life clear. So instead here, I'm going to actually do if I do something like the following, which is well, let's just do this. This is the one I want. And then we'll do something like the following, xlab. This is exactly the same. This is exactly the same. Actually, let's just do this. Okay, this is it. This is one that I had in the notes. I'll give you. This is it. This is the other example. These two calls are identical. I hope. Okay, I'm typing it. But these are identical. They end up with exactly the same matched arguments. Okay, and that's the key thing. All we're trying to do is take all the arguments here and get them into that environment to set so that the call frame can then be established, and then we can move on with evaluating the body of the code of the function scatter.smooth. So what are we going to do here? Let's go through this argument again. Step 0 doesn't matter. We don't look at the arguments. Step 1, take all the named arguments. LPARS again. Main doesn't match anything here, so let's actually just hold that out for the time being. Okay. Now let's do partial name matching. Well, fam matches family uniquely, okay? There's no ambiguity, okay? So now what I do is I take fam and I map it over into the family over here. Again, not taking, in this case it's a literal value, so I don't need a promise, but I just put in a literal value. What about XL? Which one does that map to? Pardon? XLab? XLim? Where's XLim? No, no, that's, okay, so I'm going to do partial matching. This matches, there's no xlim, so there's no ambiguity, okay? It matches xlab, okay? And dot, 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 if we match something before dot, 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 partially, that guy wins. Okay, what about YL? Problem, because it matches ylab and ylim. This is where R will give you an error. R will say it's ambiguous. I'm not going forward. Just forget it. Yep.
So the position of the dot 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 is important.
We are getting there. This is, so by the way, just as fun, in one of the exercises for this, I needed to find a function with this characteristic to illustrate this point that actually that L parse is after dot dot dot. That's a very important issue here. We're coming to that soon, but yeah, the position of dot 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 is very, very important. Okay, nearly always it's at the end. And I say dot 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 is basically says, give me any other arguments. I'll take them all. I don't care. Okay, and I'll do something with them. Oftentimes, we'll just see what's in them and process them one at a time, generically. Or in other cases, we'll say, look, I don't want those arguments, but I'm going to pass them directly on to another function. So I might have a function of my superplot, like scatter.smooth, which draws a plot. I want you to be able to specify things like main and any other graphical parameter. But I'm not going to do anything with them. I'm just going to pass them straight on down to plot. Okay? So dot, dot, dot is a way of sort of saying, oh, just give me all this stuff, and I'll just pass it straight on. Or if you, where else do we use dot, dot, dot? Here's an example. Let's take the sum, or mean is the same thing. Just give me anything you want. I'll process them all at the same time. Okay? I'll treat them all as one big collection of numbers. Okay? So we use them for two different purposes. Okay. So this will not work. That will work, because now YLA uniquely maps to YLab. Okay, so what's the step? What have we done? Set up the environment in step 0 with the default values as promises. Then we do exact matching. So we now sort of say, okay, here are all the arguments. Well, for the exact matching, we set this one and we eliminate it. Okay, now that's it. We've only eliminated one. Now we go through and we've eliminated fam, and mapped it to family. We've eliminated xlab and ylab and set those values. And that means we have a bunch left. Okay, and now what we're going to do with the ones that are left, we're going to go back in and put them, we're going to match them to the parameters over here in order, in the order they appear. Okay, without having excluded all the other ones. Where's my pen? Okay, so what did we actually match? So this is for call number 2. L parse is gone. Okay, that's matched. Then we matched xlab and ylab. We matched family. Okay, and was that all we matched? Fam, xlab, ylab, L parse, and main. We have main. We didn't. Main. What do we do with main? It's a named argument. It didn't exactly match anything. It didn't partially match anything, so it goes in here. So this gets main. Okay, so main is now checked off. So what's left? Okay, that means we've got this guy and nothing else. So what do we have left? So now they go in order. We've got x, y, span, and whatever else evaluation haven't been set. But now x gets this guy here. Okay, x gets our, what was it, MPG, square bracket, comma, C of MPG, and weight. Okay, and that gets that guy, and that's what's going on. This is how R does the matching. If you don't know what it's going to match to, how would you do this?
You would call the function. You would look at what the function actually is.
And then do the matching yourself? It's hard. It's actually hard. So there's a function that does this for you. Okay, there's a function called match.call, and you say match.call of scatter.smooth, and here, let's quote this. Okay, so actually let's just do this. Okay, so let's just do this. I'll show you. This is another reason why, so match.call of scatter. Again, do you need this? Only when things go wrong. Okay. And I'm going to do this, okay? And now that's what I get back. And now notice that it's completely expanded all of the argument names for me, and it's matched them up, and it's got it correct. And what I've done here, just to be clear, I've said match.call of here's the definition, here's the call. What if I had left the quote out? I have this weird thing called quote paren, and then the actual command. What if I just let, well, but this is the simplest thing to do when you, is just do it. You can't break anything. Okay? So let's just remove this. Oh, I got a plot. Why? Because I gave R an expression and it evaluated it and then handed the result to scatter.smooth. I need to say, look, here's a call, but I don't want you to do the usual thing you do with it, which is to evaluate the call. I want you to just treat it as a call. So I could parse this, or I can just say quote it, just escape it essentially. Just, okay? So that's what happens when I do this, and then I manage to do something weird. Okay, so so if I go back and so this is what we end up with. Okay, this is the actual matching that goes on. Okay, match.call will actually do it for us, but you should know how to do it in your own head. So there's a simple rule that how many of you have ever set the how many of you have used the value t instead of true? Oh, come on, I know the rest of you have to. Okay, so those of you who have, okay, I've shown you why it's not a great idea. 99% of the time it just works. It's that 1%, and that's the real hassle. You know, well, I'll never think to look there. The right way to write code, correct, the best way is to spell out every single argument name fully, okay? And just use step 1 here, that we just exactly match the parameters and arguments by exact name. So you spell out x equals, y equals, this, that, okay, on and on. That's the most explicit way to do it. It'll save you a fraction of time. It'll lose you a fraction of time. It'll lose you personally time, but it'll be very clear what's going on. Okay, so when things don't work, you know, it's a problem. If I just show you this, where did I put it? So let's say it here. What about this guy here? What happens to this? This is a simpler version. Scatter.smooth of x, y, family. Now what's going to happen is, and I did this yesterday, I was just trying to construct a simple example, and this thinks that I'm trying to plot this against this, and that this then should become my span, and then that this should become my family, and it goes, I don't understand the sequence of numbers as a family, that's all wrong, and I get a weird error, and you go like, well, it's blatantly obvious to me, but here the x and y are matching early on to the x's, and the y's in the call, and that's bad news. Okay, so that's actually what is happening. Everyone clear on this? Yep.
How does it find the y within the x?
Okay. Okay. So also, what does it do with these? What does it do with these? When in the other example we had here. Okay, so let's take a look at this guy up here. Not only that. What about these guys here? If you actually go in and look at these, what it's actually going to be is it's a name. Okay, let's go back to our friend, this weird name that we've never seen before. This actually will be, in this call, there will be a name, and the name will have the value empty quotes. Okay, so, and then what does it do with that? And it just kind of magically assigns it over here. So when it gets to that, when it tries to evaluate that, it says, go find the variable name nothing. It's like, oh God. Well, this comes back to our lazy evaluation. We may never ever need those names. Okay, and in this case, R is basically saying when you put in nothing, we're actually leaving the default values here. Okay, but also we may actually end up never needing certain things. Okay, so I'm getting to your question. All right. I'm not completely ignoring you. Now, so So this is not so, this is simple, okay, but there are 3 steps. This is why I just want to just emphasize 4 steps. Step 0 is just set up the call frame, then do the exact name matching, then do the partial name matching, and then whatever's left over, whatever parameters are unfilled, whatever arguments aren't, go in the same order, okay, until they're gone. Not every parameter will get a value, and it may look as if it needs a value, okay? You'll find functions for which you need a value. Just before we get to your question, okay, and I'll make sure I do, let me just emphasize this one thing. If I have another if I went and found a function that was built into one of the packages that comes with R that has ... in it, and that has another argument, or sorry, another parameter that is afterwards, and this is slightly weird. Do any of you know of another function that does this, has this? I went and found one, because I can programmatically go and search for these things, because I can rip these functions apart in R. It's it's 2 lines of code to actually get to find all the names of these functions. Does anyone know of another function that has ... and then an argument name? Yeah, well, I just showed it to you. Somebody was paying attention. Okay, there we go. See? Okay, read table and ... Okay, it has strings as factors and stuff like that. Okay, here we go. What happens here? So here. This is the simplest example. Let's call sum of 1 and 2 and NA. Okay, and NA.rm equals true. What's the answer? 3. Okay. Okay. 3. Explain that. These are great mental exercises for understanding R. Okay, I mean, just like, let me try this. And if you can construct the counterexample, you go, got it. I now understand.
The same value of 1 to the true, and then just takes that numerical value and adds to the sum of 1 and 2.
The answer is it's going to add 1, 3, and 1. 1, 2, and 1 to get 4. That's how we got there. Now, that's what R sees. Now, let's go back over here. Okay, what does it do? Let's look at it. It creates a call frame with 2 parameters, ... and NA.rm. Okay, it sets up the default value for the second one, which is true, as a promise. Now, then it does step 1 of the matching. Here's a named argument. Okay, does it exactly match any of the parameter names here? No. Okay, fine. Step 2. Let's do partial matching. Does it do partial matching? Yes, but there's a very special rule that says after the ... you don't do partial matching. So the fact that the ... comes before this means that this does not partially match that parameter name. If I'd flip them around, it would be fine. But this is a gotcha, okay? And there's good reasons for it, because we don't quite know what's going to happen to the ... so that picks up stuff, okay? But so that's what's actually going on here. So this NA.R actually ends up going into the ... and then the sum takes 1, 2, and true. And what we'll talk about on Thursday is true turns into 1, because to make them all consistent with each other, they all have the same type, it will coerce a logical up to the numeric value here. By the way, these are numeric vectors, not integer vectors. They look integers. Everyone thinks they're integers, but they're not. They're numeric unless you, and if you ever wanted them to be an integer, you would put an L at the end of the literal value to force them to be. It's a funky little thing. Okay, so that's what's going on. So this thing is this thing can be a real annoyance. Okay, that if you don't explicitly match the full name of this thing, then bad things happen, and it goes into the ... and then we have to find out where that ... is going to be used. Is this clear? So,
flipping it didn't, I still got 4.
Pardon?
When I flipped it, I still got 4.
No, sorry. If you flip it, so there's a 1. I'm going to give you a hard time just because. So what's it?
The 2, the 1 and 2, and then the NA.R.
No, I'd have to flip the parameters. So it would have to be in the definition of the function. Okay, so that's where the it is important. This is why it's really important to differentiate between the call and the arguments and the function definition and its parameters. If I flipped these two guys around in the definition of the function, then we could use partial matching for the first one. But boy, wouldn't it be really annoying to say sum of 1, 2, oh, hang on a second, I have to go back and say false always for this guy. So that's why it's done this way. Okay, everyone happy? Anyone happy? I'm happy. Okay. Okay, so what we've done is matching. So now let's get on to where the heck is this happening, and we'll see two different things. Okay? So let's take a look at scatter.smooth as an example. I just chose this because of that one thing. Look what's happening here. Okay? So this is kind of weird. Okay? So what we do is we say x and y. Now remember, we didn't give it a y. We gave it, in our call, we had this MPG of these two things. And by the way, does anyone want to go off and figure out how to match these? Remember, this is a call. This is square bracket. Okay, square bracket. So this turns into, why do I always put the pen over here? Okay, let's take a few with me. Okay, so this here again, just to be clear, this turns into the call square bracket backticks, okay, of MPG and then of nothing, the empty name, and then MPG and weight. No problem. So how do you match the call? How do you match those? How do you match these parameters? You have to do the same thing. Again, this is R. It's okay. So how do I get the square? How do I get to look at the square bracket function? I need the backticks because otherwise it'll just be sitting here going, duh. Okay. Actually, it won't, because it's totally broken to even say this without something in front of it. Okay, so there we're okay. We won't be sitting there with the plus sign coming back on. You're not finished yet, but we get an error. So stop it. Okay, so now we use the backticks. Okay, this is great. There we go. Ooh, now there's a funky one. Okay, so everything's a function call, but there are some weird ones. Okay, this one is especially weird. Okay, so let's just take a quick look at the help. Hello, what are we doing? Oh dear. I just switched back to using ESS, so I'm not used to using ESS, and it doesn't like me doing this. It wants me to use their help system. We can actually go in and take a look, and this is basically going to have X and then ... Okay, as the thing. Actually, it's not. It's going to have this thing. This square bracket operator. The function definition is basically, it's a function with X, I, J, and ... Okay? And this is going to be X, this is going to be I, and that's going to be J. Okay? Because there's no named arguments, and we're going to match in perfectly fine. Okay? And that's what's going to happen. How do you know this? This is weird. You have to look at the documentation to actually find the names, the matching names. Okay? Anyway, let's go back up to here. So we've got all our calls, we got, okay? So by the way, just to be clear, what's going to actually happen at some point, and I'm not going to tell you when, but at some point what is going to happen is we are going to have this call frame, and if this isn't clear, please let me, if I need to draw it more carefully. At some point, we are going to go ahead and evaluate this call. At some point, we need the data. Okay, it'd be great if we could magically just keep going down and get the right answer without actually doing the computations, but that's a little bit beyond us at the moment. So, we've set up this call frame, and at some point, we're going to make this call frame, so it's going to create another call. And this is going to be now to another environment, but for the square bracket operator. Okay? And then we're going to match the names. So we're going to set up xij ... And we're going to match all the arguments. Then we're going to evaluate this call. And this is going to magically return a value. And then this guy will disappear. Okay? It'll happen somewhere here. And I'm being intentionally vague. It'll happen somewhere in this line. Okay? Okay? And actually, what's going to happen is we're going to get a call like this. XY dot coords. And then we're going to get another call, which is square bracket of this guy up here. Okay, this is going to return, then this is going to go do its business. This will call other functions, and we'll get, this one will have disappeared. This guy will introduce new calls. They will disappear. Then eventually this one will finish and then return its value and assign it over to XY. This will disappear, and then we'll move on to the next line, and another call will happen, and it will have subcalls. So we'll have this sort of accordion of call stack coming back, moving on, another call stack. So at any moment in time, there will be a sequence of calls in effect. This is named the call stack, and it's a sequence of call frames, environments, and we have to figure out where R is going to look for everything, but that's what's going to actually happen. And if you're curious as to why, is there something odd there? I said, we're going to call this, create the call frame, and then we're going to actually create a call frame for X. That seems to be out of order. In any other language, we would evaluate X, and then hand it, we'd get all of the, we get evaluate X, Y, X label, Y label. We get them all together and we go, okay, now, here we go. And we throw them off to this function, and we'll be done. But I've said basically what's going to happen is we're just going to call this. And X doesn't exist yet. But remember, I got a promise to X. So when somebody actually wants the value of X, well, it's the guy inside X coords who's going to refer to, and this may be called A down in XY coords. He's going to go like, hey, I need you now. And then R is going to go back up and say, I will now deliver on my promise. And it will then go and evaluate it. Okay, so that's why we will set this call frame up first. Then somebody will reference the first argument to this XY coords. And then we actually have to go back and create it, which makes it very weird. When you look at a call stack, you may be in a very weird order. You may actually be looking at something that you think should have happened ahead of time, but actually is happening after you got there. And you go, okay, my head hurts now. And we'll talk about this when we talk about debugging, but this is one of the critical things.
So just to clarify, it's creating in each of these accordion call frames, it's creating the promise, or it's running the promise, but not until it's gone through and done all those accordions, and at the very end, does it go and execute that? No, good question, very good question. No, what we can actually do is we're going to actually, I'll try to, I have a simple example where we can actually go and look at this and actually see exactly when it's happening. What's happening is, and you can walk your way through this, okay? This is the nice thing. You can actually watch R do its thing and say, stop and show me when you're about to do something, and that's great. What's going to actually happen, and I'm making this up as I go along, but I'm pretty certain I know what's going to happen. Remember, X over here now in our function definition, as we're going, what happens when we're trying to, let me just back up. When we're trying to evaluate a function, okay, a function call, a call to a function, we go through this step 0, step 1, step 2, and step 3 to match all the parameters and arguments. Okay, we've got the matching now. The next thing we do is we actually take the body, each of these, this is just a list of calls, okay? So we wander our way through this one at a time, and we just evaluate each expression, okay, or each call, okay? And that's all that's going to happen. So I'm saying that when we get to this line here, okay, when we get to this line here, there is a call to XY coords, we construct this. Now, I'm going to have to go, so we have to do all the name argument matching. Okay, the parameter matching. So if we want, and R has to do all this for you, if you want to say xy.coords, that's its definition. Okay, so great. We do the matching again. There was no names, so it was just simple positional matching. So we know X corresponds to that MPG square bracket and so forth. Now, it says if is.null of Y. So we've already set up the promise, okay? So what's even weirder here, if you want to think about it, is this thing here, X, is a promise to this. This thing here is a promise to this thing, which is a promise to this thing, okay? Okay, we do a lot of promising, okay? But we deliver, okay? So when this comes in, okay, it says if is null.y. Okay, so have we talked about X yet?
who knows? I might sort of say, look, you didn't give me a y. I couldn't care less about x. I'm out of here. In which case, if that command over there, npg of this guy, is actually a command to go and read 10 terabytes from disk, okay? Oh, and by the way, you didn't give me a y. I don't need it. I'd be kind of annoyed if you just, well, why didn't you tell me that beforehand? And that's one of the nice things that this deferred evaluation allows you to do. It says, if I don't refer to it, you don't need to do the computations. Okay? So this is one of the benefits of laser. You had a question?
That's supposed to be empty cars in case.
Empty cars. Sorry. Thank you very much. Sorry. Thank you. Sorry. Sorry. They're in my notes, but yes, thank you. This is, sorry. Yes, I'm trying to transcribe what I remember from my notes. Thank you there. It's otherwise, actually, it wouldn't matter in the sense that it's just, we'll go find a variable, and this is a literal name that we're going to use for subsetting. So it could actually be MPG inside MPG, but that's another matter. Thank you very much for correcting that. Thank you. Okay. Okay. So this is fine. So here we're now in XY coords. So we get down to here, and then we say, is that thing? Still haven't mentioned x yet, have we? Still haven't mentioned x. Now we mention x. The second we touch x, we say, I need x. So it says, go and evaluate the promise. Which promise? So it goes back up, and it looks, remember, x is in here as a promise. Exactly analogous to here. We have a promise to what? To this promise up here. And this promise goes back over to here. So promise, great. Okay, so now we look at it and we find out that it's a call to square bracket. And now we do all the argument matching, and then we actually execute this code. So that's why this call frame is actually after XY coords, or induced by XY dot coords. Does that make sense? Okay, there will be a quiz then. Okay, so so this lazy evaluation is actually kind of weird, but that's all that's going on. That's all that's going on here, is that we're just basically saying until x is referenced, we don't need it. And this is why, see, to answer your question now, we're basically saying, okay, if there's no y, well then, what we're going to do is we're going to basically assume that x is a matrix or a data frame. We're going to pull out the first column and the second column, and now we're done. So we can go on and we can start doing all sorts of things, even though values are missing. Okay, what we can actually do here is if we go back up to here, see this one, we can sort of say, yeah, y has a default value of null, but is it missing? Which is different. Not is it null, but the person told me it was null, actually said use null, but here it says null. If they didn't tell us it was anything, we can query that. Okay, so we can do a lot of different things. So this is why R can be somewhat confusing, because it has a default value, and yet we can actually replace the default value knowing that it's missing and with a different value, which is altogether weird. But that's all that's actually going on here, is we're just going through executing these lines of code, okay? And through this magic of lazy evaluation, we're only executing the commands when they're needed. And that's of all of these guys. Tell me this, and this is hard, this is tricky, okay? What's the best way to do this? This is scatter.smooth. Where does R find the definition for xy.coords? This is where it's all very straightforward, actually. It goes through the environments. Which environments? Search path? No. That would be a train wreck. Okay, because now, here's my let's call it, here, I'm doing some simulations, here's some calculations, here are the XY coords equals this. It would find your XY coords in your global environment, because that's what you gave the name to some intermediate result that you did. That wouldn't be a problem, because you created a data frame. I mentioned this earlier. R is smart enough to know it's looking for a function, so it'll skip that one. But then you attach some ridiculous package that somebody's trying to learn how to write R, and they say publish a package with the xy.coords, and they sort of do some seriously silly things, and R will find that one if it looked along the search path. Nope. This is very important. That, remember environments? Remember I sort of said, you don't need to know about environments now, but you will later on, so let's talk about them early on. That's the environment. So it will walk its way through the environment ancestors, but not the search path. Okay? So what it'll actually do, and I'll show you this in a second, okay? We'll actually go, but let's do this sort of conceptually. What it will actually do is it'll, you know, remember, it's going to evaluate this. The evaluator looks at this, and it says, okay, this is a call. Well, first of all, it's an assignment to this thing. So what does it do? It does the right-hand side first. There's no point in actually figuring out where you're going to, what variable you're going to assign it to in case it fails. That's a waste of time. So it evaluates this first. So remember we said this is the same as 1 plus 2. It goes and finds the function being called, xy.coord, so it has to search. It finds it. Then it has to go and actually get the arguments. Where does it find the arguments? It finds the arguments. It first looks in its call frame. What if it doesn't find them? It looks in its parent environment. And that tells us something about the parent environment of this scatter.smooth. Okay, because I only want one rule. It's really annoying if I come in and sort of say, oh yeah, well, if you're at the top level, this is the way R works. But if you're not, if you're in a function, oh, it works differently. So, you know, that means when you actually change from one line of code and put it in a function, you have a totally different computational model. That would be a train wreck. No, we want one single rule. Okay, so what happens is, this is my call frame. We will look for xy.coords in the call frame. We will look for X in the call frame. We will look for Y in the call frame. We'll look for everything in the call frame. But when we fail, we'll walk up the parent to the parent environment. And what's going to happen is, because this function, okay, is defined, the actual general scatter.smooth, and this is somewhat, I'm going to try to be entirely technically precise, and I want you to actually pay attention to the difference, I hope. Okay? The function is defined in the stats package. This is a call to the function. It's happening at the top level command, so okay, that's fine. But what we do is we create a call frame for each call to that single function. And when we create this call frame, we create a brand new environment, and its parent is the environment of this function, i.e. the stats package. And lo and behold, if we walk our way through, the stats package has its parent environment is actually all of the things it imports from other packages. And after that, it goes on to another set of environments and eventually ends up in base. Okay? So it will be able to chain its way through and find all of these different things.
So that means it has multiple parents?
No, it only ever has one parent. It's very simple. It only ever has one parent. Otherwise, we wouldn't know what to do, and I'd have to tell you, if you don't go down one path and then then come back and go down this path. No, it just has one parent at any moment in time. Okay? It's a clever scheme that actually allows us to implement it with single parents. Okay? Trust me. They are very much linked. They're chained together, but you can come in and we have different ways of doing it. But that's it. You're right. You would think we need multiple things, but we get away with it in a particular implementation technique. But so we can talk about that if you care. Okay. Okay. So the answer is we're just going to actually wander our way through and find it. This is why we're going to avoid the search path. We will not look on the search path for xy.coords here. This is because this is in a package. Do you have functions that are in a package? Okay, many of you will just write a little function in the global environment. If you take it, so let's just do that. Let's just quickly do the following. Okay, so xy. What's the environment of scatter.smooth? So this is not the call frame. Okay, this is not the call frame. This is the environment of that packet of this function. Okay, what I've told you, I'll show you if you really insist on me showing it to you. When I create a call frame to that function, I'll get a brand new environment, and its parent will be this guy. Okay, and if I look, and as I wander my way through this, I can chain my way up. Parent of this guy, that's this guy. Okay, what's the parent of this? It's base. What's the parent of that guy? Oh my God. This is weird. Base, this version of base actually now goes back onto the search path. Okay, but that's okay. But you'll never actually utilize this. But watch this. F is a function that takes A and B, and it just returns A plus B. What's the environment? This is in my global environment. So what's the environment of F? It's the global environment. Go back to what I said. When I call F, I will get a brand new call frame. What's its parent going to be? It's going to be the parent. It's going to be the environment of F. Okay, so we just sort of say, oh, you're a particular call to F. You get your own little environment. But to make sure that you can find all the things that F can find, I'm going to put the parent environment of F. Sorry, I'm going to put the environment of F as your parent, and now you'll be able to see everything. Let's just go in and actually just do this, which is, let's debug F of 1 and 2. Okay, I'm now sitting in F. I am sitting, we're doing debugging now, okay? We are now sitting right here in the call frame for F. We've already matched all the arguments, okay? LS. We got A and B. Actually, let's just do this. Okay. What is the value of B? It's a promise. It doesn't have one yet because I haven't done anything, because I haven't yet to refer to B. If I look at B now, I'll evaluate it. Okay, so if this was going to take 20 minutes to if this was going to take 20 minutes to compute this, because it's a huge command, just looking at it, just asking what type it is, will actually, means I have to go and evaluate it. Okay, but I'm basically sitting here. So now, how do I get a hold of the call frame? I told you you can actually do an enormous amount of discovery on your own. Sys.frames is the entire call stack that's currently in place. I've only got one. It's the F. If I'd set up another function that called F, I'd have two. My first function that called F. Okay, let's take a look at this. Let's take a look at the very first one here. Let's take a look at the LS. There's my A and B. Okay. So what's the parent.environment of this? It's the global environment, okay? And that's how this is going to find the plus. It's going to now search the global environment, then its parent, so it's walking along the search path. When I'm back in my scatter.smooth, I'm searching along a different sequence of environments. Is this clear? It is cryptic. If this is clear, we've wasted our time, because then you all knew this ahead of time. The point is, it takes a little bit of time to digest, I suspect. There's very few rules here. Okay, that's the thing some of us like about this language, is there's very, very few rules. You only have to learn those rules, and then you can reason about absolutely everything. But as I mentioned, this is pretty powerful with the lazy evaluation and the partial name matching and so forth. There are these steps to understand how a function call works. But as I mentioned, everything's a function call, so therefore if you've got that, you understood. Yes? Do you want that microphone?
No. No. Could you possibly throw the script on the web?
Which script? This whole transcript? Yeah, I will more than happy. I'll save this. Remind me just to save it, and I'll put all of this up. I would say I've gone through this in my notes, which I tried to explain this, and if there's anything that's unclear, I would love to know about it. I'd like to actually sort of refine these notes so they stand alone and are clear. Yes.
So when do the promises get evaluated? So like with the X, can you show us?
I can. I will show you now. I'll show you now in a second. I'm just trying to think of the simplest way to do it. I have some examples that I can show you. Before I get there, okay, there's something about the promises that you don't care about, but this all just 99. The purpose of my saying I'll do this is partially just because I don't know what's being done elsewhere, and this is not the only way to learn R. It's kind of a nice way to relearn R's technical stuff so that you can reason about things when you get into trouble, okay? Or when you're trying to write software or whatever it is, where that you actually understand the computational model. When I get this promise down here, that's this guy here, MT cars. Where does this guy find MT cars? This. By the way, it will never. What? Oh, that was just a line to say. By the way, I'm not rewriting this. This is actually somewhat. This actually requires a little bit of clear-mindedness and clear thinking. For one, there are languages. The original S language used to do this. It would actually be here and would look up here, and that is nonsense. Okay, it's convenient for certain things, but nonsense. So if you can't find X, Y coords in here, here, you look up here. Okay, that's very bad news because now where you find things depends on who called you. It's like, oh God, that's really bad news. Okay, but here, I said this is out of order. So what actually happens is this is actually at the top level command. I typed this in, said scatter.smooth of MT cars. I meant MT cars starting in the global environment. When we construct the promise, we remember where we were. Okay, so we know to go back there. So this promise actually says, oh, by the way, that promise is at the global environment. Okay, the promise down here. So if we pass an argument down here and that's constructed here, the promise goes back to this call frame. So it always remembers how to get back. It does keep things clear. But you've got to remember where all of these evaluations are actually happening. So you want to see where this happens. So let's just do the following, okay? Debug of scatter.smooth, okay? We'll take this example. Okay, so this is how we debug. We're debugging for a very specific purpose here, which is actually to see when a calculation occurs. Okay, so this is slightly different, although it can be very useful. Okay, so what I'm actually going to do is, let's go back over to our call. This is our call. Okay, so we want to actually see when, we're going to see when X is things. So what I'm actually going to do is I am going to debug this guy here. And this could be an absolute train wreck. Okay, I'm not going to do this. Okay, I'm going to make life slightly simpler. Okay. Okay, so Alex, sorry. Okay, and again, actually coming up with ways to test to see if you understand something or to query something basically allows you to understand it. Okay, actually coming up with the test, essentially. It's a wonderful way of thinking of this. What I'm actually going to do is I'm going to put in a call to rnorm of 10, okay, and another call to rpos of 10, okay? So this way, okay? And now what I'm going to do is I'm actually going to, so this way, I'm going to debug the rnorm, and I'm also going to debug rpos. Okay, these are for generating random numbers from these two different distributions. So now, when I run this command, there I am. I'm stopped. I am now directly, I'm sitting, R has already constructed this call frame for scatter.smooth. I can look at it. Remember, I can go and get the sys.frames. I can look at its parent and all that. I can do an ls on this, and I can find out what all these are. They're all promises. If I ask for the value of one, I'll force that promise. So I'm not going to do that. So what am I going to do? I'm going to run the first command next. Will this guy? It's not showing me this stuff. Okay. So sorry, let me just show you what this guy is not being as well behaved as it should be at the moment. Okay, so this is the code I'm actually debugging. So we're now poised to execute this command. Does that refer to X?
Yeah.
Yeah. So this will force X. Okay. Apparently not. Okay. Anyone want to guess what's happening? Missing is very special. Okay, I did call rnorm. Missing is extremely special. Okay, missing says, if it's a promise, I'm going to leave it alone. Okay, I'm not going to touch it. Okay, I'm not going to evaluate it. Substitute of X, same thing. These are working on the language objects. They're in a very unusual way. What's this called? Non-standard evaluation. Everything I've told you doesn't work for these two functions. Okay. Okay. We need a few backdoors. Okay. We just need to be able. So the quote function is the same sort of thing. It says, quote says, oh, you know, don't evaluate this. Actually, it's not quite the same. Okay, I was saying that it breaks everything. What it's using is lazy evaluation. It says, don't evaluate this. Oh, and I'm just going to return the same thing without evaluating it. Okay, that's what the substitute does. Substitute basically says, don't do it. Okay, substitute and quote are almost the same thing, except for substitute is way more powerful because we can actually change. We can substitute other elements into the call. Okay, so that's fine. So these two are very special. So now the next line is going to be, that's that line, that's that line. We're now poised to call XY coords. So we're in the red box where we're currently in. Would you like to see the calls? There we are. That's the call. sys.frame, sys.call. We can see where we are, which is really weird. Any function can actually go back and look at who's called it, maybe change how they behave depending on who's called it. Okay, they can do all sorts of weird things. But we're sitting here now. So now let's do N for next. Okay, and now we're in R+. Huh? Why not R norm? Because it should have been R norm first, shouldn't it? So we're going to do this again because we needed to do one more thing. We needed to stop in xy.coords to see what was going on because we're now just running xy coords. So we stopped in scatter.smooth, but we need to stop and then see what's going on. No, because if you remember when we looked at xy.coords, it checked y first. Okay, so that's why it's executing the Poisson first before the R norm, because it's doing it in the order in which it's needed. Okay, so if we actually just we can continue this. Okay, and so if we go back over here and we get our call back up here, where was it? Come on, we're almost there. Come on, where are you? Oh, hang on a second. Let's do this other one, which was debug of xy.coords. Okay, and let's go back over to this guy. So here we are. We're down here, down here. Now we're into this xy.coords. Okay, all the way back up to the top. Oh, it's way too long a function. Okay, so there we go. Okay, if we want sys.calls. So we've got these two calls. Okay, and now we're going to next this one, next this line. Okay, now we're in here. Okay, we didn't see what was going on there. Now you see what's happening. This is the sequence of calls. That's our top one, then the XY coords, and then the call to R+. And later on, this one's going to do its thing. It's going to fail because I forgot to give it a second argument for the Poisson. Okay, but basically, so if I go back over here and do this and 1, now as we wander our way through, and then we have to figure out what line that's, I think that now would behave. So now if we can do this, and now we're exiting here. Now we're about to do this. Now this is about to do an X. This is now going to refer to X. We're back. Where are we? If you want to know. Okay, we're now back in the XY coords. This is the accordion thing or whatever you want. This was the call to R+. This has now gone away again, so now we're back in XY coords, and then there'll be another one come down. That may call multiple things, and then they'll spring back eventually. Okay, and now we'll go on to the next line of X coords, which is what's happening here. So now this is poised to actually execute this command. Okay, now it needs R norm. Okay, so and sys.calls of these guys, there we are. Okay, and see it's actually checking if it's inherits of x POSIX xt. So the command we were running was this. Okay, where is it? It's this. We're actually down here. So we called inherits. So that created a new little call frame. When this comes back and says false, then we'll go down into here. Okay, will I execute X twice? that would be very bad news if I randomly generate X here and then an X here and do it again. When I evaluate this promise, I get the value and I throw the promise away and say, that's X now. Okay? So these are all promises. These are all promises until they're evaluated, and then they actually have the real value. So we don't do it again. Okay? And so off we go. Okay, so now we're in our norm, and now we're just going through this. Okay, so the lazy evaluation is causing us to do Y before X, because that's the way the things work. Okay, and if I'd wanted to, so we could actually make this example slightly more interesting, which is we put in lambda here. Okay, and we put n equals 10 here, and we put n here, and n here. So now if we wander our way through this, okay, now we wander our way through. Here we are. Okay, always use that thing. Okay, so here we are. If we wanted to, we could actually take a look and see what we've got. But now we're in the XY coords. Okay, and well, let's just do the following, which is so. This is a tricky one to actually show. This one I can't get access to directly here. I need the promise. I actually need my pause on the promise, which is in C code, to actually go and see what's its environment. And now we'll see that the environment of this call to our norm, its promise, is the global environment, and that's where we'll see n. And if I assign lambda in the global environment, that's where it will find lambda. Okay, because it has to know how to go back there, and R takes care of all that for us. Is this clear at all? It's actually. Can anyone want to? Anyone wish to summarize? No. Okay. So let me just try to summarize this way. Okay. Calling a function. Remember, we had to find the function first. Then we just actually went and created this call frame, did all the matching of the arguments through exact name matching, partial name matching, dealing with ... and arguments after that, and then filling in the ones by position. Okay, it's a 3-step algorithm. Okay, that things. Then where do we find things? We find it in the call frame, or the parent of the call frame, which is the environment of the function definition, which is either the global environment if it's your function that's not in the package, or it's the package's environment, and that's how we go and find everything. And that's why the same approach works no matter where the function is defined. It has a parent environment attached to the call frame, and life is good. There is this weird thing called lazy evaluation, okay? And it just basically says, we do not actually do the computations until you do something. So, you know, okay, just to be entirely perverse here, don't ever, ever, ever do this, okay? Unless you want to actually have fun with your friends, okay, to actually just annoy them. Here's the sort of thing I could do. So I call our norm of n, okay? I call scatter.smooth. Okay, blah, blah, blah. Now, imagine that the first line of scatter.smooth is to change the value of n in the global environment. Okay, I can do that. Okay, I can screw around and change absolutely anything you want. In which case, this will not be the n in the original. At the time I called it, it'll be n when I find it, when I actually go back and search for it. So you can do very nasty things. That's why one of the very important things about R in, again, almost every case is R functions have no side effects. This is what's called functional programming, okay? If you take it to its absolute extreme, so there's languages like Haskell and things like that, they're beautiful programming languages. If you take it to its natural extreme, it can't actually return a value, because that would be a side effect, okay, of actually printing it on the screen or something like that. So it can do all these computations, and then I can't tell you the answer, okay? But it's a wonderful paradigm which basically says when R gets past a value, we make a copy of that value, and the caller cannot see any modifications to that object from then on. unless you give it back to that person and they get to put it somewhere, okay? In other words, okay, so there's no side effects. So a function cannot reach back up and change n in its parent, or say, oh, I need to return 2 values, but I can only return 1. Let me just put the other one in my secret password. Okay, no, I use that variable for something else. Actually, you can't do that. Okay, the called function should know nothing about the parent, and the parent should know nothing about the called function except for what its inputs are and what the argument and the parameter names are. And then they should communicate only by the inputs and the outputs immediately returned. And therefore, we avoid any global variables, especially assigning results into global variables. Global variables are just a bad thing, okay? Without doubt, okay? The only global variables that are not so bad are the ones that never change. They're constants, okay? But even then, there's better ways to actually program where you can still make them parameters, but the default values. So, but this is absolutely critical. R passes everything by value. What? Okay. What doesn't get passed by value? What is mutable? Environments. So don't pass environments down. Okay? Environments are the one thing I can make a change, and the guy holding the same environment will see make copies to that same thing. They will actually see the changes. Whereas if I pass down x to scatter.smooth, if I pass down a vector of empty cars $mpg, just a vector, and if that guy throws all the missing values away and multiplies everything by 2, I will never see that. That's his copy, and this is a really good thing. It basically means that, so one of the problems when you're writing C code or Python code, when you pass by references, you have this massive call stack. Remember what's going on? This guy is calling this guy, and then coming back up, and then this guy calls a few others. There's hundreds and hundreds of things in effect. Who changed? I come back, and all of a sudden, X has changed. And you go like, who changed X? And you spend hours trying to find out who changed X. Okay, and then you eventually go, well, you weren't supposed to change X. That's the bug. Okay, so this is a much cleaner style of programming. There is a downside to it, which is that you're making copies of absolutely everything. So if you've got a terabyte of data and you pass it down, and somebody says multiply everything by 2, you've now got 2 terabytes of data, and so on and so forth. Okay, R is a little smarter than this. Okay, it uses this thing called COW, copy on write. So if you just pass it down, it doesn't make a copy. But if you change anything, it'll go, quick, separate and make a copy. Okay? And there are clever ways to avoid some of this stuff, but you don't care about it. But the key thing is that these guys are not modifying anything else. I told you you can. There are backdoors built into this system to do everything. So you can assign into any environment that you want any variable and eliminate it. You can check to see if it's already there. You can multiply it by 2 just to piss somebody off. You know, hey, every time around I'm in a loop from 1 to n, I'm just going to keep multiplying n by 2. They'll never finish. Okay? You know, you can do all sorts of stuff, but people don't do that. And if they do, if you're ever using these things like get and assign, you're probably doing the wrong thing. Okay? So this pass by value or functional programming is absolutely critical. I think there is, as I mentioned, one of the reasons people like to be able to modify the incoming arguments is because I can only return one thing. You only return one object in R, okay? And by default, you don't need a return. You don't need a call to return. It is the last value. It is the value of the last expression that is returned. Okay, so that's fine, but it can only be one thing. But if you need to return 2 things, what do? You just combine them into one list, and then the caller gets them and has to extract the 2 pieces together. You know, to extract them and make them separate if they care, or they pass them on or whatever. But you don't get into this game of I'll return 10 things, okay, and they all get assigned back onto different variables. That's just a bad thing. There is this one other thing that so this is all we've talked about with calling functions. It's, you know, we've spent a long time on basically this is the R evaluator. There's nothing else going on in the core of the language. There is this one nice little thing. If you open a file in a function, you should close it. Or we'll eventually close it through garbage collection and all that sort of stuff. But you should close it because you can actually get yourself into trouble by opening too many files and it says, I've run out of file descriptors. here's another example. If you create a temporary directory and it's got gigabytes of data in it, when you're finished with it, you should clean up yourself. R doesn't know to do that until the end of the session. Even worse, when this does happen, if you're drawing plots, then sometimes it's just easier to change the global graphics parameters inside your function, like change the aspect ratio to be square as opposed to use the entire screen, or just change the fonts or whatever it is. And then you finish your function. You should reset the graphics parameters so that the next person who goes along, and so you're drawing a map, you need the aspect ratio to be square, and then all of a sudden somebody else is drawing a nice little plot, and a scatter plot, and it takes up this much space. And it's like, what the heck's going on? Okay, you should reset the parameters. How do you do that? Well, basically, before you return, you just reset the parameters. But you may never get there. That's the problem. First of all, you may have 3 returns. If this, do that, then return. If that, do something. It can be very complicated, so you may actually have lots of returns, and then you need to put the same block of code in each place. And you could call a function to do this, but it's actually a little tricky. Sometimes it can be a little annoying. So what you actually want to do is you want to say, hey, I don't care where you return from. When you finish this function, execute this code. So what we do is things like we do things like the following. So let's do the following. So let's do long.r, okay? So f equals function. We'll just do something silly, okay? We'll say on.exit. We'll say print cleanup. Okay, and now we're just going to do sys.sleep of 2. Okay, so this is F. Okay, there we go. And it does the right thing, okay? Now, let's do the following. Okay? I interrupted that function. I did not let it terminate. Okay? I just said zap it, just kill it. Okay? So it never got to actually do it would never get to my cleanup code. Okay, it would never get to return. So if I'd written it like this, which is the way most people would initially write it like this, okay, most people would just write something like this, do everything, print, and then return true or something like that. Okay, whatever. Okay, and we don't need the return. Okay, so just do all the hard work, then do the cleanup. This is proxy for do some calculation and then just return. But my trouble is I never let it, the user interrupted this. Well, my code will never get to this line of code. Okay, so that's bad news. So now you've left terabytes of data on disk. You may have a connection going to some URL asking the website for humongous amounts of data, but you actually want to terminate that connection so it doesn't continue to utilize those resources. This one will actually take care of, no matter how I finish this, no matter how I terminate this function, except for one condition, no matter how I terminate this function, okay, I will call this code, whereas this one will not. Okay, and obviously if I have multiple ifs and else's and all that sort of stuff, I can put this one line up here and it will always happen before I return. This is a useful thing to do, this on.exit. There is one exception as to when this code will not get run, and it's basically when R terminates before it actually gets to finish this function, okay, at all. And that means that if it crashes or there's an earthquake and your laptop dies, you know, so these are basically extreme situations where R is no longer there, okay? So it can't be blamed for not finishing it. The actual R process died. So in that regard, this is a very, very useful thing to do. But this is basically what happens in functions. We are just about to return here, and R basically grabs this value, executes this code, and then returns the actual value to the caller. And that's how functions work. Does anyone have any questions? You've been quiet, or else I'm talking too much.
Can you clarify one thing? What's interrupting it here?
Me.
It's not in the code. It's just like you're saying stop this.
This sys.sleep basically just goes to sleep for 2 seconds, and when it's finished, it'll go on to the next line, which is nothing, and it returns. But if I you know, we can put a long loop in here if we wanted to. I'm just basically going here. So here's F. So if I see how long it takes 2 seconds basically to do its thing. Whereas if I do this and immediately hit Control C, I'm terminating it. Okay. It also interrupts me and asks me, do I want to look around? Unfortunately, normally this would just be, normally it would just terminate immediately. Let me just do this, just to make the point clear. See, now it didn't get the 2 seconds. Okay, it didn't get to 2 seconds, but it still printed its cleanup. Is that clear? But I am interrupting it. Alternatively, I just get an error. Okay. You know, let's do something like this. Here is another example. So that's not you. I wanted the other guy. Okay, so let's just do the following. On exit of print cleanup. Okay, so that's fine. So we say this, and then I'm going to execute the. Okay, I don't have a variable named Danielle. It's going to get an error. Okay, so if we just, okay, I got an error, but I still got the cleanup. So it actually failed in this command, in this line, and that means I'm out of here. I'm gone in the function. Oh, but I got one last thing to do. Regardless of how I exit this function, I have to get out. Okay, and that's, there we go. Okay. I've written a lot of this stuff down. I will put the links up. Hopefully it's not too much there. It's just wandering through. It would be great if you guys could actually just read this and just say, okay, I get it, or come back on Thursday with questions about, and we can do this all over again. You know, not quite. Because this is really, they're very fun. I mean, this is just the heart of R. Okay. Then there's issues with the data types and data structures as to how they get, you know, coalesced together and coerced into different types and different subsetting facilities and stuff like that. And then there's a lot about the debugging, which we actually kind of hit today. I also would really like to know what you guys would like to talk about. So we've got four sessions scheduled. We can fill them all. We don't potentially we don't have to cover everything. There's an enormous amount to R. There's also very little to R, as I tried to explain. We can talk about namespaces and all that sort of stuff, and packages and writing that. But it'd be great to know what you guys want to know more about. But we will on Thursday. I plan to do the data types and the subsetting primarily. And so any feedback would be terrific. And I will see you on Thursday at 9. Yeah.
So we don't have an outline for the sessions of the next week.
I do, but I want to get some input as to what things you guys would like as well. But
would you be able to post it so that we will see what are the things that are available and
yep.
Kind of
Sure. Yeah, but I don't. But there are things that won't be